Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to spend some time with one of the strangest objects ever imagined by modern physics. Not a black hole, not a neutron star, not even one of those giant galaxies that seem to stretch forever across the darkness. Instead, we're exploring something that sounds almost like a mistake: a white hole. If you've heard of a black hole before, and chances are you have, then you already know the basic idea. A black hole is a place where gravity becomes so powerful that nothing can escape. Not planets, not spaceships, not even light itself. Everything can go in, nothing can come out. A white hole, at least on paper, appears to do the exact opposite. Nothing can go in. Everything can only come out. It's a concept so unusual that many physicists have spent decades arguing about whether such an object could ever exist at all. Some think white holes are merely mathematical curiosities. Others suspect they might hold clues about the deepest workings of the universe. A few have even wondered whether our entire cosmos began as something remarkably similar to one. And that's where tonight's journey begins. But before we wander too far into the strange corners of space and time, I'd love to ask you a simple question. Where are you listening from tonight? Maybe you're curled up in bed beneath a warm blanket. Maybe you're watching from a quiet apartment in the middle of a city where distant traffic still hums beyond the window. Perhaps you're listening from a small town where the night is calm and the stars are visible overhead. And while you're thinking about that, here's another fitting question. If someone handed you a door that only opened one way, what would you expect to find on the other side? Most of us probably imagine a doorway we can walk through, a passage from one room to another. Yet the object we're discussing tonight is stranger than any ordinary door. Imagine standing before a doorway that constantly throws things outward. Light pours through it, matter pours through it, energy pours through it. But the moment you try to step inside, the doorway refuses. No matter how hard you push, no matter how fast you move, entry is impossible. The universe says no. That's the basic picture of a white hole. At least it's the picture that first captures people's imagination. If you find this little expedition soothing, intriguing, or simply a pleasant way to wind down after a long day, I'd be ever so grateful if you gave the video a like and perhaps subscribed as well. It helps this quiet corner of science reach others who enjoy drifting off with a few cosmic mysteries before sleep. Now then, get comfortable. Let your shoulders relax. Allow the day to slowly settle behind you. Because the story of white holes begins somewhere very familiar. It begins with black holes. The funny thing about white holes is that almost nobody starts by looking for them. People usually discover the idea accidentally. You see, black holes already sound strange enough. Imagine compressing a tremendous amount of matter into a tiny region of space. The gravity becomes stronger and stronger. Eventually, a boundary forms around it. A point of no return known as the event horizon. Cross that boundary and escape becomes impossible. Even light, the fastest thing in the universe, cannot get back out. For generations, black holes occupied a special place in both science and imagination. They were cosmic traps, giant gravitational pits, endpoints of massive stars. Then physicists began doing something physicists are very good at. They started playing with equations. The equations themselves, as it turns out, often care very little about human intuition. Sometimes they reveal possibilities nobody expected. Sometimes they reveal things nobody asked for. And occasionally they reveal ideas so bizarre that scientists stare at them for decades, wondering whether nature actually allows them. White holes belong firmly in that last category. The remarkable thing is that nobody originally sat down and said, let's invent an object that spits everything out. Instead, white holes emerge from mathematics. To understand why, imagine watching a movie. In the film, a glass falls from a table and shatters on the floor. Everyone watching immediately recognizes what happened. Gravity pulled the glass downward, the impact broke it apart. Nothing unusual there. Now imagine reversing the footage. Suddenly shards leap from the floor, they fly upward, they reassemble themselves perfectly. The glass lands gently on the table. The reverse scene looks wrong. Not impossible according to the basic laws governing individual particles perhaps, but certainly wrong according to everyday experience. Our brains immediately notice that time appears to be moving backward. White holes have a somewhat similar feeling. A black hole consumes matter. A white hole appears to eject matter. A black hole pulls inward. A white hole pushes outward. A black hole accepts everything. A white hole accepts nothing. It's almost as though someone took the movie of a black hole and pressed rewind. And that naturally raises a question. Can the universe really work in reverse like that? Or are we simply being fooled by the mathematics? The deeper scientists looked, the more complicated the answer became. What's especially fascinating is that white holes aren't just strange because of what they do. They're strange because of what they imply. Most objects in the universe interact with their surroundings. Stars absorb gas, planets collect dust, galaxies merge with other galaxies. Everything participates in a kind of cosmic exchange. Things move, things collide, things influence one another. A white hole seems unwilling to cooperate. According to its theoretical description, nothing from outside can enter. Not a single atom, not a beam of light, not even a wandering particle drifting through space. The white hole simply continues ejecting whatever it ejects while remaining inaccessible from the outside. If that sounds a little antisocial, you're not alone. Many physicists have wondered how such an object could survive for even a moment in the real universe. After all, space isn't empty. Despite appearances, it's filled with particles, radiation, and debris. If a white hole truly rejected everything attempting to enter, it would behave in a way unlike anything we've ever observed. That's one reason astronomers remain skeptical. The cosmos has given us plenty of black hole candidates. We've photographed shadows around them. We've detected collisions between them. We've watched stars orbit them. Black holes appear everywhere. White holes, meanwhile, remain elusive. No telescope has ever pointed toward an object and confidently declared, "There it is. That's definitely a white hole." Not once. And yet the idea refuses to disappear. Partly because the mathematics remains intriguing. Partly because certain modern theories keep finding ways to bring white holes back into the conversation. And partly because they force us to think differently about some surprisingly big questions. Questions like, what happens inside a black hole? Can information truly disappear? How did the universe begin? And perhaps most importantly, is there a limit to what space and time themselves can do? Those questions may sound enormous, but that's one of the pleasures of astronomy. You can begin with a simple curiosity and end up examining the foundations of reality itself. A person might start by asking how stars shine. Before long they're discussing nuclear fusion, then particle physics, then the origins of matter, then the Big Bang. One question quietly opens another. White holes operate in much the same way. At first glance they're merely odd objects, an interesting cosmic novelty, a black hole's opposite twin. Yet once you start pulling on the thread, the entire fabric of modern physics begins to move. And speaking of fabric, there was a time when scientists weren't even sure black holes existed. Today that sounds surprising. Black holes appear in documentaries, movies, textbooks, and news articles. They're practically celebrities of the astronomical world. But for many years they were regarded with suspicion. Some physicists believed they were merely mathematical artifacts, strange solutions appearing in equations without any physical counterpart. Nature, they argued, would surely find some way to avoid creating them. Reality couldn't possibly be that weird. Reality, however, had other ideas. Evidence accumulated, observations improved. Eventually, black holes transformed from theoretical curiosities into accepted members of the cosmic family. That historical lesson remains important, because whenever scientists discuss white holes, a small voice inevitably asks, what if we're making the same mistake again? What if today's mathematical oddity becomes tomorrow's discovery? Nobody knows. And that's what makes the subject so enjoyable. Science isn't merely a collection of answers, it's also a collection of carefully examined uncertainties. A map with regions still marked, here be dragons. White holes occupy one of those regions, not because they're proven, not because they're likely, but because they're interesting enough that physicists haven't entirely given up on them. If anything, recent years have made the discussion even more lively. New ideas about quantum gravity, new theories about the interiors of black holes, new attempts to reconcile relativity with quantum mechanics. All of these developments have created opportunities for white holes to reappear in scientific conversations, not as established facts. Not as confirmed discoveries, but as possibilities worth investigating. For tonight, though, we don't need to rush ahead. The reference script we're following taught us something valuable. Big ideas become easier to understand when approached slowly, one careful step at a time. So before we begin talking about Einstein's equations, collapsing stars, wormholes, or the origins of the universe itself, it helps to spend a little longer with the central image. A cosmic door that only opens outward. Nothing enters. Everything exits. Simple words. Extraordinary consequences. At first glance, a white hole seems wonderfully easy to understand. If a black hole pulls things in, then a white hole must push things out. If a black hole traps light, then a white hole must release light. If a black hole is cosmic intake, then a white hole is cosmic exhaust. Simple, neat, almost suspiciously neat. And that's usually the first clue that something in physics deserves a closer look. The universe has a habit of punishing oversimplifications. What seems obvious from a distance often becomes much stranger when examined carefully. White holes are a perfect example. Most people encounter the concept for the first time through a very straightforward description. A black hole is an object from which nothing can escape. A white hole is an object into which nothing can enter. That definition isn't wrong. The problem is that it creates the impression that white holes are merely black holes with a plus sign swapped for a minus sign. As though nature simply decided to manufacture both versions and scatter them around the cosmos. One vacuum cleaner, one leaf blower, case closed. Yet the actual story is considerably more complicated. To see why, imagine you're standing near a black hole. This is not recommended for a variety of reasons, but let's pretend you have an exceptionally durable spaceship and a strong sense of adventure. From a safe distance, a black hole doesn't look like a giant hole in space. That's one of the biggest misconceptions. There isn't a dark tunnel hanging in the sky. There isn't a cosmic drain swirling like water disappearing down a sink. Instead, there's a region where gravity has become so intense that escape is impossible once you cross a certain boundary. That boundary is called the event horizon. The event horizon is one of the most important concepts in modern physics, because it represents a point of no return. You can move toward it, you can cross it, but once you're inside, every possible future path leads deeper inward. Nothing gets back out. Not rockets, not signals, not light. The universe has effectively closed the exit. Now imagine reversing that situation. Not metaphorically, literally. Imagine taking every process associated with a black hole and running it backward. Instead of matter falling inward, matter emerges outward. Instead of light disappearing, light bursts forth. Instead of objects crossing a horizon and becoming trapped forever, objects encounter a horizon they can never cross from the outside. Suddenly, you've created something resembling a white hole. This idea sounds almost reasonable until you stop and think about what it actually means. Suppose a white hole exists somewhere in space. Imagine it ejecting matter continuously. Perhaps streams of particles, perhaps radiation, perhaps entire clouds of gas. Whatever emerges, it keeps emerging. Now imagine a tiny speck of dust drifting nearby. Ordinary dust, nothing dramatic. Eventually that dust attempts to approach the white hole. What happens? According to the theoretical description, it cannot enter. Ever. The white hole's horizon acts as a one-way barrier. Everything moves outward, Nothing moves inward. That may sound manageable when discussing a single grain of dust, but space contains a lot of dust, and gas, and radiation. And particles. The universe is messy. Things collide constantly. Stars shed material. Galaxies interact. Cosmic rays travel enormous distances. The entire cosmos is a giant arena of interactions, which raises a troubling question. How does a white hole survive in such an environment? The moment anything touches it, problems begin appearing. This is one reason physicists became skeptical very quickly. A black hole is relatively easy to imagine forming. Take a massive star. Allow gravity to win. The star collapses. Eventually a black hole appears. The process is dramatic but understandable. Astronomers observe stars. Astronomers observe supernova explosions. Astronomers observe collapsed stellar remnants. The pieces fit together. But what creates a white hole? That's much harder to answer. You cannot simply run nature backward. A broken glass doesn't leap from the floor and rebuild itself. Smoke doesn't return neatly to a candle wick. A spilled cup of coffee doesn't politely jump back into its mug. Many physical processes possess a preferred direction. That direction matters, and white holes seem to demand precisely the sort of reverse behaviour we almost never observe. This became clear shortly after scientists began exploring the mathematics more deeply. The concept itself emerged during attempts to understand solutions to Einstein's equations. Those equations, as we'll discuss later, describe gravity not as a force but as the curvature of spacetime. Mass bends spacetime. Spacetime tells matter how to move. It's an elegant framework, remarkably successful, and occasionally surprising. Sometimes the equations produce solutions that correspond beautifully to reality. Sometimes they generate possibilities that leave physicists scratching their heads. White holes belong firmly in the second category. They emerged naturally from certain mathematical descriptions of black holes. The equations seemed perfectly happy to allow them. Nature, however, remained suspiciously quiet. No observations, no confirmed detections, no clear evidence, just mathematics saying, "This could exist," and astronomers replying, "Perhaps, but where is it?" That disagreement has persisted for decades. What's fascinating is that the disagreement isn't really about the mathematics. Most physicists accept that white hole solutions can exist within certain theoretical frameworks. The real debate concerns reality itself. Does the universe actually make such things? That's a very different question. Physics has encountered this situation before. Mathematics often predicts possibilities long before observations catch up. Sometimes the predictions turn out to be spectacularly correct. The planet Neptune was discovered after mathematical calculations suggested something unseen was affecting Uranus's orbit. Antimatter appeared in equations before scientists detected it experimentally. Even black holes themselves spent many years living primarily inside mathematics. So being theoretical doesn't automatically disqualify an idea. At the same time, mathematics can produce solutions that never manifest in nature. An equation might allow something without requiring its existence. Think of it like architecture. A blueprint might describe a perfectly valid building. The building could exist. That doesn't mean anyone actually constructed it. White holes occupy a similar position. The blueprint exists. The construction remains uncertain. The uncertainty becomes even more interesting when we consider how humans instinctively think about opposites. We're accustomed to pairs, north and south, positive and negative, matter and antimatter, action and reaction. The mind naturally expects symmetry. If black holes exist, shouldn't white holes exist too? The idea feels satisfying. Nature often displays symmetry. Unfortunately, nature is under no obligation to satisfy human expectations. Some opposites exist, others don't, and occasionally the apparent opposite turns out not to be opposite at all. White holes create exactly this kind of confusion, because while they are often described as opposites of black holes, the relationship isn't perfectly symmetrical. A black hole can form through known physical processes. A white hole lacks such a straightforward origin story. A black hole grows by consuming matter. A white hole faces challenges simply remaining stable. A black hole fits comfortably into modern astrophysics. A white hole remains an outsider. It's less like a twin and more like a mysterious cousin. Nobody is quite sure belongs in the family photograph. Another difficulty involves predictability. Imagine discovering a black hole. Astronomers can estimate its mass. They can model its effects. They can study objects orbiting around it. The behaviour follows understandable patterns. A white hole presents a different challenge. What exactly emerges from it? How much matter? How much energy? For how long? Why that material rather than something else? The theory becomes murkier. Questions multiply rapidly. Answers become less certain. This uncertainty contributed to white holes developing a somewhat unusual reputation within physics. They're respected enough not to be dismissed entirely, yet they're controversial enough that many researchers remain cautious. Mention black holes at a scientific conference and few eyebrows rise. Mention white holes and conversations become considerably more animated. Some researchers see fascinating possibilities. Others see mathematical artifacts. Still others occupy a middle ground, remaining open-minded while demanding stronger evidence. That cautious attitude reflects something important about science. Good science isn't merely about finding exciting ideas. It's about determining which exciting ideas survive contact with reality. And reality can be surprisingly unforgiving. A theory might appear elegant. A model might seem beautiful. An equation might behave perfectly. Yet if observations refuse to cooperate, scientists eventually move on. White holes have spent decades existing in that uncertain territory between possibility and evidence, neither confirmed nor completely abandoned, still lingering, still intriguing, still provoking questions. Perhaps that's why they continue capturing the public imagination. There's something irresistible about an object that appears to violate our expectations, a place where matter emerges rather than disappears, a horizon that rejects entry rather than trapping escape, a cosmic structure behaving opposite to one of the strangest objects already known to exist. Even the name itself contributes to the appeal. Black hole, white hole, simple words, immediately memorable, almost storybook-like. Yet beneath those names lies an astonishingly complex discussion involving gravity, space-time, thermodynamics, quantum mechanics, and the fundamental structure of the universe. The further we explore, the stranger things become. Picture yourself floating far from Earth. No cities, no traffic, no glowing screens, just darkness, scattered stars, and an ocean of space stretching in every direction. Somewhere ahead of you sits one of the strangest objects in the universe, a black hole. Today, black holes are so familiar in popular culture that it's easy to forget how astonishing they really are. They appear in movies, documentaries, video games, novels, and news headlines. We talk about them almost casually, as though they're simply another type of cosmic object sitting alongside planets and stars. But the reality is far stranger. A black hole is not a giant vacuum cleaner roaming through space. It is not a hole punched through the universe. It is not a cosmic drain swallowing everything nearby. In fact, if you replaced our sun with a black hole of exactly the same mass, something surprising would happen. Earth would continue orbiting almost exactly as it does now. We wouldn't suddenly spiral inward. The planets wouldn't be sucked away. The solar system wouldn't immediately collapse into disaster. Of course, we'd quickly freeze because sunlight would disappear, which would create its own collection of problems, but gravity itself would behave much as before. That fact often surprises people because black holes are commonly imagined as unstoppable cosmic monsters pulling everything toward them. The truth is more subtle. To understand white holes properly, we first need to understand what black holes actually are, because white holes were not invented independently. They emerged from attempts to understand black holes themselves. And once we see how black holes work, the idea of their supposed opposite becomes both more logical and far more mysterious. The story begins with stars. Stars spend most of their lives performing an extraordinary balancing act. Gravity is constantly trying to crush them inward. Meanwhile, nuclear fusion deep inside their cores pushes outward. Those two forces compete continuously. Gravity pulls, fusion pushes. For millions or billions of years, a stable equilibrium exists. Our own sun is doing exactly that right now. Every second, enormous amounts of hydrogen are converted into helium. Energy pours outward. Gravity presses inward. Neither side wins. The star survives. Eventually, however, fuel begins running low. The star can no longer maintain the same outward pressure, and when gravity senses weakness, gravity does what gravity always does. It takes advantage. For smaller stars, the result might be a white dwarf. For somewhat larger stars, the result can be a neutron star. But for the most massive stars, gravity becomes overwhelming. The collapse continues, matter compresses, density increases. Space itself begins responding to the immense concentration of mass. At this point, things start becoming difficult to visualize. Human intuition evolved to understand forests, rivers, weather, and perhaps the occasional falling rock. It did not evolve to understand space-time being crushed by a dying star. Yet that is exactly what happens. According to Einstein's theory of general relativity, gravity is not really a force in the traditional sense. Instead, mass bends space-time. The larger the mass, the greater the curvature. Objects move through that curved space-time, and we interpret the result as gravity. Imagine placing a heavy bowling ball on a stretched sheet. The surface bends downward. Smaller objects rolling nearby follow curved paths. It's not a perfect analogy, but it captures the basic idea. Now imagine replacing the bowling ball with the mass of a giant star. The curvature becomes extreme, then more extreme, then even more extreme. Eventually a threshold is crossed. The escape velocity exceeds the speed of light, and that's where a black hole appears. The phrase escape velocity deserves a moment of attention because it's central to understanding black holes. Escape velocity is the speed required to break free from a gravitational field. On Earth, rockets must reach a certain speed to escape our planet's gravity. If they don't move fast enough, they fall back. Simple enough. Now imagine gravity becoming stronger and stronger. The required escape velocity increases. At some point, the required speed becomes greater than light itself. And since nothing can travel faster than light, escape becomes impossible. Not difficult, not unlikely, impossible. This creates the feature that defines a black hole, the event horizon. The event horizon is often misunderstood. People sometimes imagine it as a physical surface, a shell, a wall, a cosmic membrane. But it isn't any of those things. If you crossed an event horizon, you wouldn't necessarily notice the exact moment it happened. No giant sign would appear, no alarm would sound, no flashing lights would announce your arrival. The event horizon is not a physical barrier, it's a boundary in space-time, a line separating regions where escape remains possible from regions where escape becomes impossible. Outside the horizon, future paths can still lead away from the black hole. Inside the horizon, every possible future leads inward. That's an astonishing statement. Not just because of gravity, but because of what it means for the concept of direction. When we think about movement, we usually imagine freedom. Forward, backward, left, right, up, down. Near a black hole, that freedom gradually disappears. Once inside the event horizon, moving away from the centre becomes as impossible as moving backward through time. The geometry of space-time itself prevents it. This is one reason black holes fascinated physicists so deeply. They weren't merely heavy objects. They fundamentally altered the structure of reality around them, and the closer scientists examined them, the stranger they became. Consider light. Light travels at approximately 300,000 kilometers per second. Nothing moves faster. For centuries, light represented the ultimate speed limit of nature, yet black holes trap it. A beam of light can move outward from the event horizon. It can struggle. It can travel at the fastest speed the universe allows, and it still cannot escape. That realization alone demonstrates how extreme black holes truly are. When something can imprison light, ordinary intuition begins breaking down. But the event horizon is only part of the story. At the center of a traditional black hole description lies something even more mysterious: the singularity. The singularity is where current equations effectively throw up their hands and say, "We don't know." According to classical general relativity, matter collapses into an infinitely dense point. Infinite density, infinite curvature, infinite gravity. Physicists generally become uncomfortable whenever infinities start appearing in equations. They often indicate that a theory has reached its limits, and that's exactly what many researchers suspect happens here. The singularity probably signals that our understanding remains incomplete. Some deeper theory, perhaps involving quantum gravity, may eventually replace the singularity with something more physically meaningful. For now, however, the singularity remains one of the biggest unanswered questions in physics, and that unanswered question becomes extremely important later when white holes enter the story. Because many modern white hole theories emerge from attempts to understand what actually happens beyond the event horizon. Before we get there, though, it's worth appreciating just how thoroughly black holes transformed from theoretical ideas into observed realities. For many decades, black holes occupied a position somewhat similar to white holes today. Interesting, mathematically plausible, not yet confirmed. Then evidence began accumulating. Astronomers observed stars moving around invisible massive objects. X-ray emissions revealed matter heating to extraordinary temperatures while spiraling inward. Entire galaxies appeared to contain enormous hidden masses at their centers. The case strengthened year after year. Eventually, black holes became impossible to ignore. One particularly remarkable example sits at the center of our own galaxy. The Milky Way contains a supermassive black hole called Sagittarius, a star. Despite containing millions of times the Sun's mass, it occupies a surprisingly compact region. Astronomers spent years tracking stars orbiting an apparently empty location. Those stars moved exactly as if an enormous invisible object occupied the center. The evidence became overwhelming. Then came one of the greatest scientific achievements of recent times. In 2019, the Event Horizon Telescope produced humanity's first image of a black hole shadow. Not the black hole itself, since black holes emit no light, but the dark silhouette created against glowing surrounding material. For the first time, something once considered purely theoretical became visible. The image was blurry. The image was difficult to obtain. The image represented years of effort involving observatories across Earth, and it was magnificent, because it demonstrated that black holes were not merely mathematical abstractions, they were real. The universe genuinely creates them. That fact matters enormously when discussing white holes. Black holes earned their place in astronomy through observation. White holes have not. Black holes explain things we see. White holes explain things we speculate about. That's a crucial distinction. Another fascinating aspect of black holes involves time itself. Remember the reference script's discussion of Einstein and relativity. Near a black hole, time behaves differently. Strong gravity slows the passage of time. This effect has been measured around Earth using atomic clocks. Near a black hole, the effect becomes dramatically stronger. Imagine two identical clocks. One remains far away, the other approaches a black hole. From the distant observer's perspective, the clock near the black hole runs increasingly slowly. Closer, slower, closer, slower. Approaching the event horizon, the effect becomes extreme. To the distant observer, the clock appears almost frozen. This isn't an illusion. It's a genuine consequence of space-time geometry. Time itself stretches. Black holes therefore affect not only space but time as well. The two become inseparable. This is why physicists speak of space-time rather than treating space and time as separate entities. Black holes reveal that the universe doesn't draw a neat boundary between them. They're woven together. And whenever one bends dramatically, the other follows. That realization leads naturally towards some profound questions. What happens to information entering a black hole? Does it disappear forever? Can anything emerge again? Does the singularity truly exist? Or is something else waiting inside? Those questions became increasingly important during the late 20th century, especially after another physicist entered the story, Stephen Hawking. Hawking discovered something astonishing. Black holes are not entirely black. Thanks to quantum effects, they can emit tiny amounts of radiation. This process, now called Hawking radiation, means black holes slowly lose energy. Given enough time, unimaginably long periods of time, black holes can gradually evaporate. That idea shocked physicists. For years, black holes had been treated as cosmic endpoints. Now they appeared more dynamic. They could evolve, they could shrink, they could eventually disappear. And that raised an even bigger question. What happens at the end? If a black hole evaporates completely, what becomes of everything that fell inside? Information cannot simply vanish according to the rules of quantum mechanics. Yet black holes seem determined to challenge that principle. The resulting debate became one of the greatest puzzles in modern physics, and surprisingly, white holes would eventually become entangled in attempts to solve it. You see, once physicists began wondering what truly happens inside black holes, some researchers started exploring possibilities beyond classical descriptions. Perhaps the singularity doesn't exist, perhaps collapse eventually stops. Perhaps matter doesn't compress forever. Perhaps something unexpected occurs deep within. And if something unexpected occurs, then maybe black holes aren't merely cosmic endings. Maybe they're part of a larger process. A process that could eventually lead us toward the strange object that inspired tonight's journey. Because the deeper scientists investigated black holes, the more they realized that these extraordinary objects were not just about gravity. They were about information, time, quantum mechanics, the structure of space-time itself. Several decades before anyone had photographed a black hole, before radio telescopes mapped the centers of galaxies, and long before the phrase event horizon became familiar to the public, a curious mathematical discovery quietly emerged from Einstein's theory of gravity. At the time, nobody was searching for white holes. Nobody was trying to invent the opposite of a black hole. In fact, nobody even knew whether black holes themselves were real. Yet hidden inside a set of equations sat a possibility so unusual that physicists would spend generations debating what it meant. And like many great scientific mysteries, it all started with mathematics behaving in a way that nobody expected. One of the strange things about science is that equations occasionally know more than scientists do. That sounds almost mystical, but it's really a consequence of mathematics being astonishingly powerful. Researchers build equations to describe reality. Then they solve them. Sometimes the solutions match exactly what they expected. Sometimes they reveal possibilities nobody had considered. And occasionally they uncover entire new categories of objects that seem almost impossible. White holes belong to that last group. To understand how they appeared, we need to travel back to the early 20th century, shortly after Albert Einstein introduced general relativity. When Einstein published his theory in 1915, it completely transformed humanity's understanding of gravity. For centuries, Isaac Newton's description had dominated physics. Gravity was treated as a force. Objects pulled on one another across space. The model worked beautifully for most situations. Planets orbited, apples fell, comets returned. Everything seemed straightforward. Einstein proposed something far stranger. Gravity, he argued, was not really a force at all. Instead, mass and energy changed the geometry of spacetime itself. Matter told spacetime how to curve. Curved spacetime told matter how to move. The result was a universe that behaved less like a collection of objects connected by invisible forces and more like an evolving geometric structure. The theory was elegant. The theory was powerful. The theory was also extraordinarily difficult. Einstein's equations are not simple. They describe how spacetime bends in response to mass and energy. Solving them can be remarkably challenging. Even Einstein himself often struggled with their complexity. That's where another physicist enters our story. His name was Karl Schwarzschild. Schwarzschild was serving in the German army during the First World War when he accomplished something extraordinary. While stationed on the Eastern Front, surrounded by the realities of war, he found time to work on Einstein's brand new equations. It's one of those remarkable historical details that almost sounds fictional. Imagine someone helping reshape our understanding of the cosmos while serving in a military campaign, yet that's exactly what happened. In 1916, Schwarzschild discovered the first exact solution to Einstein's field equations. The solution described space-time surrounding a perfectly spherical mass. At first glance, it seemed straightforward, but hidden within it was something deeply strange. The mathematics predicted a critical radius, a special boundary. Cross that boundary and space-time behaved very differently. Today we recognize this as the event horizon of a black hole. At the time, however, nobody quite knew what to make of it. Even Einstein remained skeptical. Many physicists suspected the strange behavior reflected a mathematical problem rather than a physical reality. After all, the solution appeared to contain singularities. Certain quantities became infinite, and infinities often signal trouble. So for years, the strange features lurking inside Schwarzschild's solution received relatively little attention. Scientists focused on more immediate questions. The world had wars to fight. Quantum mechanics was emerging. Astronomy was rapidly evolving. The peculiar implications of black hole mathematics remained largely in the background. Then something interesting happened. As researchers continued exploring Einstein's equations, they realized that the Schwarzschild solution contained more structure than originally recognized. The equations seemed to allow additional regions of spacetime, additional possibilities, additional geometries, and among those possibilities sat something that looked astonishingly familiar to modern eyes: a white hole. The discovery wasn't immediate. It emerged gradually as mathematicians and physicists examined the equations more deeply. One of the challenges involved understanding apparent singularities. Some singularities were genuine. Others turned out to be artifacts of the coordinates being used. A useful analogy involves maps. Imagine trying to represent Earth on a flat sheet of paper. Certain distortions inevitably appear. The map contains problems, but the problems belong to the map, not the planet. Similarly, physicists realized some apparent pathologies in the equations reflected coordinate choices rather than actual physical features. As better mathematical techniques developed, new aspects of the Schwarzschild solution became visible. Researchers eventually discovered that spacetime could be extended beyond the original description. The geometry contained regions nobody had initially recognized, and one of those regions behaved like the reverse of a black hole. Matter could emerge. Nothing could enter. The object seemed to eject rather than consume. Suddenly, the idea of a white hole appeared, not because anyone demanded its existence, not because observations required it, simply because the equations allowed it. That distinction is important. White holes were not invented to solve a problem. They emerged naturally from mathematical exploration. The equations themselves suggested the possibility, and that immediately created a dilemma. How seriously should scientists take it? Physics has encountered this dilemma many times. An equation predicts something strange. Researchers must decide whether nature actually uses that possibility. Sometimes the answer is yes, sometimes the answer is no. and sometimes it takes decades to find out. The history of antimatter provides a useful comparison. When Paul Dirac's equations predicted antimatter, the idea initially seemed bizarre, yet experimental evidence eventually arrived. Nature turned out to be even stranger than expected. Could white holes follow the same path, some physicists wondered? Others remained unconvinced. The problem wasn't the mathematics. The mathematics worked. The problem was physical plausibility. White holes appeared extraordinarily fragile. A black hole makes intuitive sense once you understand gravitational collapse. Matter falls inward, density increases, an event horizon forms. Everything follows a logical progression. White holes seemed different. Where did they come from? Why would they exist? How could they remain stable? The equations offered possibilities. They did not necessarily offer realistic formation mechanisms, and formation matters. A theory isn't merely required to describe an object, it must also explain how the object appears in the universe. Stars explain stars, supernovae explain neutron stars, gravitational collapse explains black holes. White holes lacked an equally convincing origin story. That made many researchers cautious. Yet, the mathematical beauty remained difficult to ignore. One reason physicists kept returning to white holes is that they appeared connected to another fascinating concept: wormholes. Today, wormholes occupy a special place in science fiction. They appear as tunnels through space-time, shortcuts connecting distant regions, gateways allowing rapid travel across enormous distances. The reality is more complicated. Nevertheless, wormholes emerged from serious physics. And intriguingly, some early descriptions linked black holes and white holes together through hypothetical bridges in space-time. The idea was roughly this: matter falls into a black hole. Instead of ending at a singularity, it passes through some kind of tunnel. Eventually it emerges elsewhere through a white hole. The black hole acts as an entrance, the white hole acts as an exit. It's an appealing image, simple, elegant, memorable. Unfortunately, nature rarely rewards us merely for finding an idea appealing. Later analyses revealed major difficulties. Most wormholes appeared unstable. Many collapsed too quickly. Others required exotic forms of matter that may not exist. Still, the connection between black holes and white holes became firmly embedded in theoretical discussions, and that connection helped keep white holes alive as a subject of scientific interest. Even researchers who doubted their existence often found themselves encountering white holes while investigating other questions. Questions about gravity, questions about space-time, questions about singularities, questions about quantum mechanics. In that sense, white holes became scientific neighbours of many important ideas. You didn't necessarily need to believe in them, but you frequently encountered them while exploring nearby territory. Another reason white holes continued attracting attention involves symmetry. Physicists love symmetry. Nature often displays it: positive and negative charge, matter and antimatter, rotations, reflections, conservation laws. Symmetry appears everywhere. White holes seem to offer a kind of symmetry for black holes, a mirror image, a reverse process, a mathematical counterpart. The temptation was obvious. If black holes exist, perhaps white holes should exist too. Yet history repeatedly teaches that symmetry alone does not guarantee reality. Some mathematical symmetries correspond beautifully to nature, others remain purely theoretical. The challenge lies in determining which is which, and that challenge became increasingly important as black holes themselves transformed from speculative concepts into observed astrophysical objects. During the 20th century, evidence for black holes accumulated steadily. Observations improved, theoretical models matured, astronomers identified compelling candidates. Eventually, black holes became accepted components of the cosmic landscape. White holes, meanwhile, remained trapped in a curious position. Their theoretical foundations remained intact, yet observational support never arrived. Decade after decade passed. Still nothing. No telescope detected a convincing white hole. No observation demanded their existence. No measurement forced astronomers to include them in standard models. They remained possibilities rather than necessities. Even so, something remarkable happened. The story refused to end. New generations of physicists continued finding reasons to revisit the idea, not because the original Schwarzschild solution suddenly became more convincing, rather because modern physics began confronting deeper problems involving singularities, problems involving quantum gravity, problems involving information, problems involving the ultimate fate of black holes. And once again, white holes started appearing in conversations. The old mathematical curiosity refused to disappear. Part of the reason lies in an uncomfortable truth. General relativity is extraordinarily successful. Quantum mechanics is extraordinarily successful. Yet the two theories remain difficult to reconcile. Each works beautifully within its own domain. Together they create tension. Black holes sit directly at that intersection. Gravity becomes extreme. Quantum effects become important. Existing theories begin showing their limitations. Whenever physicists attempt to bridge that gap, strange possibilities emerge. White holes often reappear among them, not necessarily as permanent objects sitting quietly in space, not necessarily as stable astrophysical structures, but as transitional states, as temporary phases, as components of larger processes. The role changes, the idea survives. And that's perhaps the most interesting aspect of white holes. Their history isn't a story of steady acceptance, nor is it a story of complete rejection. Instead, it's a story of persistence, a mathematical possibility discovered within Einstein's equations, questioned repeatedly, doubted repeatedly, re-examined repeatedly. Each generation finding new reasons to ask whether the equations might be hinting at something real. For now, though, one fact remains clear. White holes did not originate in science fiction. They did not emerge from wild speculation. They appeared because Einstein's description of spacetime allowed them. The equations opened a door. The question ever since has been whether nature actually walks through it. Imagine for a moment that astronomers announce a remarkable discovery. Not a new planet, not a distant galaxy, not even another black hole. Instead, they reveal that somewhere in the universe they have found an object that continuously ejects matter and energy, while refusing to let anything enter. A genuine white hole. The news would likely spread across the world within hours. Scientists would scramble to verify the evidence. Observatories would point every available telescope toward the object. Physics departments would become very busy places, and perhaps most importantly, everyone would start asking the same question. What exactly are we looking at? Because while it's easy to describe a white hole as the opposite of a black hole, that phrase only scratches the surface. Once you start imagining what a real white hole would actually do, things become very strange very quickly. A black hole, despite its exotic nature, behaves in ways we can understand. Matter falls inward. Gravity dominates. Energy accumulates. The process follows familiar physical principles. A white hole turns that picture upside down. Instead of consuming matter, it produces matter. Instead of trapping light, it releases light. Instead of acting as a destination, it behaves like a source. And that distinction changes everything. Let's begin with the simplest question imaginable. What would a white hole look like? Oddly enough, the answer isn't obvious. A black hole appears dark because light cannot escape. A white hole should be the exact opposite. Matter and radiation emerging from the object would likely make it extraordinarily bright. Potentially brighter than entire stars. Perhaps brighter than entire galaxies for brief periods. Every particle leaving the white hole would carry energy. Every photon would contribute to an outward flood of radiation. From a distance, astronomers might initially mistake such an object for some kind of violent cosmic explosion. That possibility creates an immediate challenge. The universe already contains plenty of violent explosions. Supernovae erupt. Gamma-ray bursts flash across billions of light years. Quasars release astonishing amounts of energy. Active galactic nuclei blaze from the centers of galaxies. Astronomers regularly observe events that release immense quantities of radiation. So if a white hole appeared, how would we distinguish it from everything else? That's one reason white holes have proven difficult to identify. Even if nature produced something resembling one, the object might initially masquerade as a more familiar phenomenon. Yet a true white hole would possess one characteristic unlike anything else: consistency, or perhaps more accurately, impossibility. Imagine standing near a volcano. The volcano ejects ash and molten rock. Yet if you throw a stone toward it, the stone enters the volcanic system. The exchange works both ways. Matter leaves, matter enters. The same principle applies almost everywhere in nature. Stars emit light but absorb gas. Planets radiate heat but collect dust. Galaxies expel material but also acquire it. Nature generally allows interaction. A white hole breaks that pattern. Matter leaves, nothing enters, ever. That requirement creates one of the biggest difficulties in the entire concept. The universe is not clean, it's not empty, it's not organized. Space may appear vacant, but it contains particles almost everywhere. Hydrogen atoms drift between stars. Dust clouds wander through galaxies. Cosmic rays travel enormous distances. Photons flood the universe from countless sources. Everything moves. Everything interacts. Now imagine placing a white hole inside this environment. Immediately particles begin approaching it. Photons approach it. Dust approaches it. Gas approaches it. And according to the definition, none of them can enter. The white hole somehow prevents every interaction. This is where many physicists begin feeling uncomfortable. Not because the mathematics fails, because the physical situation becomes increasingly difficult to imagine. How does the white hole maintain such perfect exclusion? How does it prevent every incoming particle from crossing its horizon? Why doesn't accumulated material destabilize the system? These questions have no universally accepted answers, and the more researchers examined them, the more challenging white holes appeared. Still, let's assume for a moment that nature somehow solves these problems. Suppose a stable white hole exists. What would we observe? One possibility is a continuous stream of matter emerging outward. Gas, particles, radiation, perhaps entire jets stretching across space. The object would resemble a fountain operating on a cosmic scale, except ordinary fountains eventually run out of water. White holes introduce another mystery. Where is the material coming from? A star uses nuclear fusion. We understand its energy source. A black hole gains mass from infalling matter. We understand its fuel supply. A white hole continuously ejecting material raises a fundamental question. What reservoir is feeding the process? The problem becomes even more striking when we consider conservation laws. Physics takes conservation very seriously. Energy cannot simply appear from nowhere. Matter cannot magically emerge without explanation. Every effect requires a cause. Every output requires a source. So if a white hole spits matter into the universe, where was that matter previously located? The simplest answer sounds almost unbelievable. Perhaps it came from somewhere else. This possibility became one of the reasons white holes became associated with wormholes. Imagine a tunnel connecting distant regions of space-time. Matter enters one end, matter exits the other. The entrance behaves like a black hole. The exit behaves like a white hole. Suddenly the bookkeeping becomes easier. Nothing is being created. Matter is merely moving, entering here, exiting there. It's an elegant idea. Unfortunately, elegance and reality are not always the same thing. As physicists investigated wormholes more carefully, enormous difficulties appeared. Most wormhole solutions proved unstable. Many collapsed before anything could pass through. Others demanded exotic forms of matter unlike anything known in nature. The theoretical bridge remained fascinating, its physical existence remained uncertain. Nevertheless, the connection persisted, and for many years one of the most common ways of imagining a white hole involved seeing it as the exit point of some deeper space-time structure. That idea carries a certain intuitive appeal. After all, if something continually emerges from a white hole, perhaps the material originated elsewhere. Perhaps the white hole is not generating matter. Perhaps it is releasing matter delivered through hidden pathways in space-time. Yet even this interpretation leaves difficult questions unresolved. How long does the process continue? Minutes? Thousands of years? Billions of years? Forever? A black hole can survive for immense periods because gravity naturally supports its existence. A white hole appears less cooperative. Many theoretical analyses suggest that even tiny disturbances might destabilize it. A single incoming particle could potentially create serious problems, and in a universe filled with particles, that's not encouraging. Some researchers therefore concluded that stable white holes probably cannot exist. If they form at all, they might exist only briefly, moments rather than ages, transient phenomena rather than permanent objects. That possibility led to another fascinating line of thought. Perhaps white holes are not long-lived structures. Perhaps they are events. This distinction matters enormously. Instead of imagining a white hole sitting quietly in space for millions of years, imagine a brief eruption, a sudden release of matter and energy, a violent burst, a temporary opening, then disappearance. The concept begins resembling an explosion rather than an object, and once physicists started thinking this way, interesting connections emerged. Because the universe contains some remarkably energetic explosions. Gamma-ray bursts, for example, rank among the most powerful events ever observed. For a brief period, a single gamma-ray burst can release more energy than entire galaxies. These events are extraordinarily dramatic. For a while, some researchers wondered whether certain unexplained cosmic explosions might involve white hole-like behavior. The idea never became mainstream. Conventional explanations generally proved more convincing. Yet the discussion demonstrated something important. White holes were evolving. Originally, they appeared as permanent opposites of black holes. Later, they began appearing as temporary phenomena. Different models, different interpretations, same underlying mystery. What happens when space-time behaves in reverse? The phrase reverse deserves special attention because it captures the essence of why white holes feel so strange. Many physical processes possess a preferred direction. A glass falls and breaks, a star burns fuel, a person grows older. These processes move one way. Not because the fundamental laws always require it, but because probability overwhelmingly favours certain outcomes. A shattered glass can theoretically reassemble itself. The laws of physics do not explicitly forbid every molecule returning to exactly the right position. The problem is probability. The event is so unlikely that it effectively never happens. White holes often feel similar. They resemble processes running backward. Matter emerges instead of entering. Order appears where we expect disorder. The universe seems to reverse course. That impression becomes even stronger when we consider entropy. Entropy is often described as a measure of disorder. More precisely, it reflects the number of possible arrangements available to a system. And according to the second law of thermodynamics, entropy tends to increase. This tendency gives time its familiar direction. Eggs break. They do not unbreak. Coffee cools. It does not spontaneously heat itself. The future generally contains more disorder than the past. White holes seem almost rebellious in this context. They appear to challenge the ordinary flow of events. Not necessarily violating physical laws, but certainly making physicists nervous. It's one thing for equations to permit a phenomenon. It's another for that phenomenon to coexist comfortably with everything else we know about the universe. And that's ultimately the central challenge facing white holes. not whether mathematics allows them. The mathematics often does. The question is whether the universe wants them. Does nature actually produce objects that continuously eject matter while refusing all incoming interaction? Or do white holes exist only as theoretical possibilities hidden inside elegant equations? No one knows, and that's what makes them so compelling. Because unlike black holes, which have largely transitioned from theory to observation, white holes remain suspended between imagination and reality, close enough to serious physics that researchers cannot completely dismiss them, distant enough from observation that certainty remains impossible. Consider the following possibility. Not that a white hole exists somewhere in the universe, not that astronomers simply haven't found one yet, but that the largest white hole imaginable has already happened, and we're living inside the aftermath. At first, that idea sounds absurd. After all, white holes are already among the most speculative objects in theoretical physics. Connecting them to the origin of the entire universe seems like the sort of thing that belongs in science fiction, rather than serious scientific discussion. Yet surprisingly, the question has appeared repeatedly in real physics, not because scientists became convinced the Big Bang was definitely a white hole. It wasn't. Rather because certain similarities proved difficult to ignore. To understand why, let's begin with the most common misconception about the Big Bang. Many people imagine the Big Bang as an explosion, a giant cosmic detonation occurring somewhere in empty space. Matter bursts outward, galaxies fly away, the universe expands into the surrounding emptiness. It's an understandable image. Unfortunately, it isn't what the Big Bang actually describes. The Big Bang was not an explosion inside space. The Big Bang was the expansion of space itself. That distinction matters enormously. Imagine drawing dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot occupies the center of the expansion. No dot is flying through the rubber surface. Instead, the surface itself stretches. The universe behaves somewhat similarly. Galaxies are not racing through pre-existing emptiness because of an ancient explosion. Space itself expands. Distances increase, everything spreads apart, and when astronomers look backward in time, they discover something remarkable. The universe becomes denser, hotter, more compact. The farther back they look, the closer everything appears. Eventually, the entire observable universe converges toward an incredibly hot, incredibly dense early state. This is where things become interesting, because black holes also involve extreme density. Black holes also involve extreme space-time curvature. Black holes also involve regions where our current understanding begins breaking down. The similarities are not exact, but they're suggestive, and whenever physicists encounter suggestive similarities, curiosity follows. One of the earliest observations people made was that the Big Bang seems to involve matter emerging outward. Everything expands. Everything moves away. Everything begins from an extraordinarily compressed state and spreads into the cosmos. At a superficial level, that sounds vaguely white hole-like. A white hole ejects matter. The early universe expands outward. The resemblance is obvious. The challenge lies in determining whether the resemblance means anything. As physicists explored this question, they quickly realized that the answer was complicated. Some similarities appeared genuine, others disappeared under closer examination. Still, the idea remained intriguing enough to investigate. Imagine observing a white hole. Matter streams outward. Energy pours into surrounding space. The object acts as a source rather than a sink. Now imagine rewinding the history of our universe. Galaxies move closer together. Stars disappear. Matter compresses. Density increases. Eventually everything approaches an extraordinarily concentrated state. It's not difficult to understand why some researchers started noticing parallels. The Big Bang appeared to represent the largest outward flow of matter and energy imaginable. If white holes eject matter, perhaps the birth of the universe shared certain characteristics. Notice the careful wording. Shared characteristics. Not necessarily identity. That's an important distinction. Modern cosmology does not treat the Big Bang as a proven white hole. The evidence simply isn't there. Nevertheless, certain theoretical models continue exploring possible connections. One reason involves singularities. You've probably noticed that singularities keep appearing throughout this story. Black holes lead towards singularities. The Big Bang appears connected to a singularity. White holes emerge from mathematical structures related to singularities. Every path seems to circle back to the same unresolved problem. According to classical general relativity, both black holes and the Big Bang involve situations where density becomes infinite. Physicists generally dislike infinities, not because they're mathematically illegal, because they often indicate incomplete understanding. When equations begin producing infinities, researchers suspect something important is missing. Perhaps a deeper theory, perhaps new physics, perhaps quantum effects becoming impossible to ignore. Whatever the answer turns out to be, many scientists doubt that nature truly contains physical infinities, and that doubt has inspired numerous alternative models. Some of those models unexpectedly revive white hole ideas. One possibility goes something like this. Suppose gravitational collapse never reaches an actual singularity. Suppose quantum effects eventually halt the compression. Instead of matter collapsing forever, a bounce occurs. The collapse reverses. Compression becomes expansion. Inward motion becomes outward motion. Suddenly the process begins looking remarkably white hole-like. This concept appears in several approaches to quantum gravity. The details vary enormously from model to model, yet the underlying intuition remains similar. Maybe singularities do not represent endings. Maybe they represent transitions. Maybe the universe has ways of avoiding infinite density. And if it does, white holes become easier to imagine. The discussion becomes even more fascinating when we consider what happens inside black holes. Classical relativity predicts continual collapse toward a singularity. Quantum gravity may tell a different story. Some researchers have proposed that matter entering a black hole eventually reaches an extreme state where quantum effects dominate. At that point, further collapse becomes impossible. Instead, the system rebounds. The black hole eventually transforms into something resembling a white hole. The implications are extraordinary. Matter falls inward. Time passes. Quantum effects accumulate. Then the process reverses. The black hole becomes an object ejecting matter. An ending becomes a beginning. A sink becomes a source. And suddenly the boundary between black holes and white holes becomes much less rigid. This idea naturally encourages cosmological speculation. If a black hole can potentially produce white hole-like behavior, could entire universes emerge through similar mechanisms? Could our own universe have originated from such a process? The possibility sounds dramatic, yet serious researchers have explored versions of it. Some models suggest that black holes might create new expanding regions of space-time. Others propose that entire universes could emerge from extreme gravitational conditions. Still others imagine cosmic cycles involving repeated collapse and rebirth. Again, none of these ideas are established fact, but they illustrate something important. White holes continue appearing because they connect naturally to questions physicists genuinely care about. Questions concerning beginnings, questions concerning endings, questions concerning what happens when known physics reaches its limits. Another reason the Big Bang and white holes sometimes appear together involves causality. A white hole presents a curious challenge. If matter emerges from it, where was that matter previously? The question sounds simple. The answer is not. In everyday life, causes precede effects. A match ignites. A flame appears, a stone falls, a splash follows. The sequence feels natural. White holes complicate this intuition. Matter emerges, but the cause may be hidden. perhaps buried elsewhere in space-time, perhaps inaccessible, perhaps existing within structures we don't yet understand. The Big Bang creates a somewhat similar feeling. Everything emerges from the early universe. But what caused the initial state? What preceded it? Was there a before? Do those questions even make sense? Cosmologists have debated such issues for decades. The answers remain uncertain. Some models suggest time itself began with the Big Bang. Others propose earlier phases. Still others describe eternal processes extending beyond observable history. White hole-inspired cosmologies occasionally enter these discussions because they provide alternative ways of thinking about origins. Instead of creation from nothing, perhaps emergence occurs from previous structures. Instead of absolute beginnings, perhaps transitions connect different stages. These ideas remain speculative, yet they reveal why white holes retain scientific interest. They serve as conceptual tools, ways of exploring possibilities, ways of testing assumptions, ways of asking whether the universe might behave differently than we currently imagine. Interestingly, one of the strongest objections to identifying the Big Bang as a white hole comes from the same issue that troubles white holes generally: entropy. As we discussed earlier, entropy tends to increase. This tendency gives time its familiar direction. The early universe appears to have possessed remarkably low entropy. That fact remains one of the great mysteries of cosmology. Why was the universe so ordered in its earliest moments? A traditional white hole doesn't automatically solve this puzzle. In some respects, it may even complicate it. The details become highly technical, but the general point is straightforward. Any successful cosmological theory must explain not only expansion, but also the thermodynamic properties of the early universe. That's a demanding requirement. Many white hole-inspired models struggle to satisfy it completely. As a result, mainstream cosmology continues favouring more conventional descriptions of the Big Bang. Yet even researchers who reject the Big Bang white hole connection often acknowledge something interesting. The comparison highlights how much remains unknown. We understand an enormous amount about cosmic evolution after the first fractions of a second. Evidence from the cosmic microwave background, evidence from galaxy formation, evidence from nucleosynthesis. The universe has provided many clues, but the very earliest moments remain elusive. The closer we approach the beginning, the less certain our theories become, and uncertainty creates opportunities for creative ideas, including white hole-inspired ones. There's also a deeper philosophical attraction here. Human beings naturally seek origins. We want beginnings. Stories usually start somewhere. Questions usually have causes. Mysteries usually possess explanations. The Big Bang challenges these instincts because it appears to represent a boundary, a point where ordinary reasoning becomes difficult. White holes offer an alternative narrative, not necessarily a correct one, but an intriguing one. Instead of a singular beginning, perhaps a transition occurred. Instead of an absolute starting point, perhaps something came before. Instead of creation emerging from mystery, perhaps mystery emerged from previous structures. Whether any of those ideas reflect reality remains unknown. Still, they continue motivating research. And that's ultimately what matters. Science advances not only through answers but through productive questions. White holes survive because they generate productive questions. Questions about space-time, questions about gravity, questions about information, questions about cosmic origins. The fact that those questions remain unresolved ensures that white holes remain part of the conversation. Not at the centre, not universally accepted, but never entirely absent. Try a simple thought experiment. Imagine you're standing in a vast forest. You need to travel from one side to the other. The ordinary approach is straightforward. You walk through the trees, cross the distance, and eventually arrive at your destination. Now imagine someone folds the forest in half. Suddenly, two distant points touch. Instead of walking for days, you simply step across a tiny gap. The journey that once required a long path becomes almost instantaneous. That basic idea lies at the heart of one of the most famous concepts in theoretical physics, the wormhole. For generations, wormholes have occupied a special place in popular imagination. Science fiction stories love them, movies use them, television shows rely on them. They appear whenever writers need characters to travel enormous distances without spending centuries crossing interstellar space. Yet unlike many fictional inventions, wormholes did not originate in Hollywood. They emerged from the same physics that gave us black holes. And perhaps most surprisingly, they became closely connected to white holes as well. To understand why, we need to return once again to Einstein's theory of general relativity. One of the most remarkable features of general relativity is its flexibility. Space-time is not rigid. It bends, it stretches, it curves. Under extreme conditions, it can behave in ways that seem almost impossible from an everyday perspective. When physicists began solving Einstein's equations in the early 20th century, they quickly discovered that the mathematical landscape was far richer than expected. The equations didn't merely describe planets orbiting stars, they described entire geometries of space-time, some familiar, some astonishingly strange. Among the strange possibilities was something that would later become known as the Einstein-Rosen bridge. The name comes from two physicists, Albert Einstein and Nathan Rosen. In 1935, they explored a mathematical solution, suggesting that two separate regions of space-time might be connected through a kind of bridge. Not a bridge made of steel or stone, a bridge built into space-time itself. The idea was extraordinary. Instead of moving through ordinary space, an object might pass through a shortcut. Two distant locations could become directly connected. Space would no longer behave exactly as intuition suggests. And once physicists began examining these bridges more carefully, they noticed something fascinating. The structure appeared closely linked to black holes. In its simplest form, the bridge seemed to connect one region associated with a black hole to another region that behaved remarkably like a white hole. Suddenly, white holes were no longer isolated curiosities. They became part of a larger picture. A black hole could act as an entrance. A white hole could act as an exit. Matter enters here, matter emerges there. The concept was elegant. Beautiful even. And beauty has always exerted a powerful influence on theoretical physics. Scientists know beauty does not guarantee truth. Nature occasionally behaves in ways that are messy and inconvenient. Still, elegant ideas tend to attract attention. The Einstein-Rosen bridge certainly did. Imagine for a moment what such a structure would mean. Suppose two distant galaxies are separated by millions of light years. Normally, even light requires millions of years to travel between them. Now imagine a tunnel connecting both locations. A traveller enters one end. A short journey follows. Then the traveller emerges on the opposite side. The enormous distance effectively disappears. From the perspective of ordinary space, the trip seems impossible. From the perspective of the wormhole, the journey remains surprisingly short. It's easy to see why science fiction embraced the concept. Unfortunately, nature soon introduced complications. As physicists studied wormholes more carefully, they discovered a serious problem. The original Einstein-Rosen bridge was unstable. Very unstable. In fact, it appeared to collapse so quickly that nothing could actually pass through it. Imagine constructing a tunnel. The moment you step inside, the tunnel seals shut. Not very useful. That, unfortunately, seemed to be the situation. The mathematics allowed a bridge. The bridge refused to stay open. This distinction became crucial. A wormhole might exist mathematically while remaining physically unusable. Nature once again demonstrated that possibility and practicality are not always the same thing. Nevertheless, researchers continued investigating. The idea was simply too interesting to abandon. Over the decades, physicists developed increasingly sophisticated models. Some explored rotating black holes, others examined charged black holes, still others investigated entirely new geometries. Many of these efforts aimed to answer a simple question: could a stable wormhole exist? The answer turned out to be surprisingly difficult. Again and again, calculations revealed instability. The tunnel pinched closed, the geometry collapsed, the shortcut vanished. The universe seemed remarkably reluctant to permit convenient pathways through space-time. Then researchers found something intriguing. Certain theoretical wormholes appeared capable of remaining open if they contained exotic matter. The phrase sounds like something from a comic book, but it has a specific meaning. Exotic matter refers to material possessing unusual properties. Most importantly, negative energy density. This concept requires a little explanation. Ordinary matter has positive energy. Stars possess positive energy. Planets possess positive energy. You possess positive energy. Theoretical wormholes seem to demand something stranger. A form of energy capable of producing repulsive gravitational effects. A kind of space-time scaffolding preventing collapse. The problem is that nobody has discovered large quantities of such material. Tiny quantum effects sometimes resemble negative energy under specific conditions, but generating enough to stabilize a traversable wormhole remains far beyond anything currently known. Consequently, wormholes occupy a curious position within physics. They're not forbidden, but they're not confirmed. They're allowed by certain mathematical models, yet no observational evidence demonstrates their existence. Sound familiar? It should. White holes occupy a very similar position. Allowed, interesting, unconfirmed. And that's one reason the two concepts became intertwined. Whenever physicists discuss wormholes, white holes frequently appear nearby. The connection becomes easier to understand if we think about flow. A river has an entrance and an exit. Traffic enters a tunnel and emerges elsewhere. Water enters a pipe and leaves through another opening. Human intuition naturally expects pathways to possess two ends. Wormholes seem similar. If matter enters somewhere, where does it emerge? Theoretical models often answer with a white hole-like region. The black hole functions as the entrance. The white hole functions as the exit. Together they create a complete system. This idea became particularly influential during the middle decades of the 20th century. Many researchers viewed white holes primarily through their relationship with wormholes. On their own, white holes seemed difficult to justify. As components of larger space-time structures, they appeared somewhat more plausible, not necessarily real, but easier to imagine. Yet another complication eventually emerged. Time. Time seems determined to complicate nearly every interesting discussion in physics. Wormholes proved no exception. Once physicists realized that wormholes might connect different regions of space-time, an unsettling possibility appeared. What if they connected different times as well? The implications were extraordinary. A traveller might enter one side and emerge not merely somewhere else, but someone else. The wormhole could become a time machine, at least theoretically. This possibility generated enormous excitement and enormous headaches, because time travel introduces paradoxes, the famous grandfather paradox, causal loops, contradictions, questions that challenge our most basic assumptions about reality. Physicists began debating whether nature possesses mechanisms preventing such situations. Perhaps wormholes collapse before paradoxes arise. Perhaps unknown laws prohibit them. Perhaps reality remains self-consistent in ways we don't yet understand. The debate continues today. And throughout that debate, white holes remain lurking nearby. Because every discussion of wormhole entrances naturally leads to questions about exits, and exits often look remarkably white hole-like. Another fascinating development occurred in recent years. Some researchers proposed that wormholes and quantum entanglement might be related. This idea gained attention through a conjecture sometimes summarized as ER equals EPR. The terminology sounds cryptic, but the intuition is fascinating. The proposal suggests a deep connection between Einstein-Rosen bridges and quantum entanglement, two phenomena previously considered entirely separate. If correct, space-time geometry and quantum information may be linked far more closely than anyone suspected. The details remain highly technical, the evidence remains incomplete, yet the idea demonstrates how wormholes continue influencing modern theoretical physics. They're not merely old curiosities, they're active participants in contemporary research, and once again, white holes often appear as part of the discussion, not because scientists have observed them, not because they have become widely accepted, but because the mathematics keeps generating them, again and again. The equations repeatedly whisper the same possibility: an entrance, an exit, a black hole, a white hole, a connection hidden within space-time itself. Whether nature actually uses such structures remains unknown. Perhaps wormholes exist, perhaps they don't, perhaps white holes accompany them, perhaps they never form. At present, certainty remains impossible. Still, the persistence of these ideas tells us something important. White holes are not isolated oddities sitting alone in theoretical physics. They're connected to larger questions. Questions about gravity, questions about quantum mechanics, questions about information, questions about space-time itself. Every time researchers explore those frontiers, white holes tend to reappear, not because scientists are determined to make them real, but because the mathematics keeps leaving the door open. And yet, for all their elegance, all their theoretical appeal, and all their connections to wormholes and space-time tunnels, one stubborn fact continues hanging over the entire discussion. No telescope has ever found one. No observatory has confirmed one. No astronomer can point toward the sky and say, there it is. Which leads naturally to the next mystery. If white holes are mathematically possible, why has the universe remained so remarkably silent about them? Take a look at the night sky on a clear evening, not with a telescope, not with sophisticated scientific equipment, just with your own eyes. You'll see stars, perhaps a few planets, maybe the faint glow of the Milky Way if you're fortunate enough to live somewhere dark. What you won't see is a white hole. Of course, that isn't surprising. You won't see a black hole either. Most of the universe remains invisible to casual observation. Yet despite decades of increasingly powerful telescopes, despite observatories on mountaintops and satellites orbiting Earth, despite humanity's remarkable ability to study objects billions of light-years away, astronomers have never conclusively found a white hole. Not one. That fact sits at the centre of the entire white hole debate, because physics ultimately depends on observation. Ideas matter, equations matter, theories matter, but eventually nature gets a vote. And so far, nature has been frustratingly quiet. The situation becomes especially interesting when you compare white holes to black holes. For many years, black holes occupied a similar position. They existed primarily in equations. Physicists argued about them. Astronomers searched for evidence. Nobody could point to a black hole and say with certainty, there it is. Then gradually the evidence began accumulating. Stars orbited invisible massive objects. X-rays emerged from strange regions of space. Galaxies appeared to contain enormous hidden masses. Eventually the case became overwhelming. Today, black holes are among the best supported exotic objects in astronomy. White holes never experienced that transition. The evidence never arrived. The telescopes kept improving. The universe kept revealing surprises. Yet white holes remained stubbornly absent. This naturally raises an important question. If white holes exist, what exactly should astronomers be looking for? The answer sounds obvious at first. A white hole should be bright, matter should emerge, energy should pour outward. Find a sufficiently energetic object and perhaps you've found your white hole. Unfortunately, the universe contains plenty of energetic objects. That's where the difficulty begins. Imagine you're an astronomer studying the sky. One evening your telescope detects a tremendous burst of energy. Radiation floods your instruments. The The signal is powerful, unexpected, remarkable. Your first thought probably isn't white hole. There are many other explanations that must be considered first. Supernovae, gamma-ray bursts, colliding neutron stars, active galactic nuclei, magnetars, quasars. The universe contains no shortage of violent phenomena. Every one of them can produce enormous amounts of energy. Every one of them can create observations that initially appear mysterious. The challenge facing white holes is not merely producing a signal, it's producing a signal unlike anything else. And so far, no observation has clearly met that requirement. Consider gamma-ray bursts. These events rank among the most powerful explosions ever observed. For a brief period, a single gamma-ray burst can outshine entire galaxies. The amount of energy released is astonishing. When astronomers first discovered them in the late 20th century, nobody knew what they were. The signals appeared unexpectedly. The origins remained mysterious. Naturally, some researchers wondered whether white holes might be involved. After all, a sudden eruption of matter and energy sounds vaguely white hole-like. Perhaps the universe was occasionally producing brief white hole events. Perhaps these explosions represented matter emerging from space-time in some unusual way. The idea attracted attention. It also attracted scrutiny. As observations improved, more conventional explanations emerged. Today, most gamma-ray bursts are understood to result from collapsing stars or mergers involving neutron stars. The mystery largely disappeared. White holes lost another potential observational foothold. This pattern repeated itself more than once. Astronomers would discover something unusual. Speculation would follow. White holes might briefly enter the discussion. Then additional evidence would arrive. Ordinary astrophysical explanations would prove sufficient. The white hole interpretation would fade away. That doesn't mean researchers were disappointed, quite the opposite. Science works best when mysteries receive explanations. The goal isn't to preserve uncertainty, the goal is to eliminate it. Still, every solved mystery left white holes with fewer places to hide. Another challenge involves duration. Suppose white holes are not permanent objects. Suppose they exist only briefly. Moments, seconds, perhaps even less. Detecting such phenomena becomes much harder. Astronomy often relies on persistence. A star remains visible, a galaxy remains observable. A black hole influences surrounding matter for millions or billions of years. Researchers can collect data repeatedly. A transient white hole would offer far fewer opportunities. Imagine trying to identify a single lightning strike occurring somewhere on Earth. Now imagine that strike lasts only a tiny fraction of a second and occurs unpredictably. Detection becomes difficult, confirmation becomes even harder. White holes may suffer from a similar problem. If they exist only briefly, astronomers might struggle to distinguish them from countless other transient events. This possibility has motivated some modern theoretical models. Rather than viewing white holes as long-lived cosmic objects, some researchers imagine them as short-lived phenomena. Perhaps black holes eventually transition into white hole states. Perhaps quantum effects trigger brief eruptions. Perhaps white holes appear only during specific extreme processes. Such ideas remain speculative, yet they offer one explanation for the absence of observations. Maybe astronomers haven't found white holes because white holes don't stick around long enough to be easily found. Of course, that explanation introduces another problem. If a phenomenon becomes sufficiently brief and sufficiently difficult to observe, how do we test the theory? Science depends on evidence. Without evidence, even elegant ideas remain conjectures. And that's exactly where white holes continue to reside. Theoretical possibility, observational uncertainty. An especially revealing comparison involves exoplanets. A few decades ago, astronomers had never confirmed a planet orbiting another ordinary star. Many suspected such planets existed. The evidence was simply missing. Then technology improved. Observations accumulated. Suddenly exoplanets appeared everywhere. Today thousands have been detected. The universe turned out to be filled with them. White holes have experienced the opposite trajectory. Technology improved. Observations multiplied. The sky became better understood. Yet white holes remained elusive. That doesn't prove they don't exist. Absence of evidence is not necessarily evidence of absence. Still, the continued lack of detection influences scientific opinion. Researchers naturally become more skeptical as years pass without observational support. Another interesting issue involves predictability. Astronomers are extremely good at identifying objects when they know what signatures to expect. Black holes create characteristic gravitational effects. Neutron stars generate recognizable signals. Supernovae follow identifiable patterns. White holes remain frustratingly vague. Different theoretical models predict different behaviors. Some suggest explosive outbursts. Others suggest continuous emission. Some propose extremely short lifetimes. Others envision more stable structures. Without a clear observational fingerprint, searches become difficult. Imagine trying to find an animal while lacking agreement about whether it has fur, feathers, scales, or wings. The search becomes considerably more challenging. White holes suffer from a similar problem. Physicists have not settled on a single observational expectation, and without consensus, detection efforts become less focused. There's also a deeper reason astronomers remain cautious. Nature has repeatedly demonstrated that strange observations do not automatically require strange explanations. A principle sometimes called Occam's razor encourages scientists to prefer simpler explanations when possible. If a supernova explains an observation, there's little reason to invoke a white hole. If a neutron-star merger explains the data, exotic alternatives become unnecessary. White holes therefore face a high evidentiary standard. Researchers require compelling evidence that ordinary astrophysics cannot explain. So far, that standard has not been met. One particularly fascinating episode occurred in 2006. Astronomers observed an unusual gamma-ray burst designated GRB 060614. The event displayed properties that didn't fit neatly into existing categories. For a brief period, speculation flourished. Some researchers wondered whether entirely new phenomena might be involved. White holes even appeared in a few discussions. Eventually, however, alternative explanations proved more persuasive. The event remained interesting. The white hole interpretation remained unconfirmed. Once again, the mystery survived, but the evidence did not. This recurring pattern illustrates an important lesson about modern astronomy. The universe is strange enough without inventing additional mysteries. Black holes exist. Neutron stars exist. Dark matter appears to exist. Dark energy appears to exist. The cosmos already contains plenty of puzzles. Scientists therefore require strong justification before introducing another exotic object. White holes have not yet provided that justification. Yet despite all these challenges, researchers haven't entirely abandoned the search, partly because the underlying mathematics remains intriguing, partly because certain quantum gravity models continue predicting white hole-like behavior, and partly because history teaches humility. After all, black holes themselves once seemed absurd. Continental drift once seemed implausible. Meteorites were once dismissed by some scientists. Nature occasionally surprises us. Ideas that appear speculative today can become accepted tomorrow. Nobody knows whether white holes belong in that category. Most physicists would probably bet against large, stable white holes scattered throughout the universe. But science is not determined by votes. It's determined by evidence. If tomorrow's observations revealed an object behaving exactly like a white hole, researchers would follow the evidence wherever it led. That's the strength of the scientific method. Opinions change, data remains. For now, though, the score is remarkably simple. Black holes, observed repeatedly. White holes, observed never. The difference matters. and it explains why white holes remain one of the most controversial ideas connected to modern gravity. The idea of a white hole sounds strange enough on its own, an object that spits matter outward. An object that refuses to let anything enter, an object that appears to behave like a black hole running backward. Yet there is another reason many physicists remain skeptical of white holes, and it has nothing to do with telescopes, observations, or missing evidence. The problem runs much deeper. It involves one of the most powerful principles in all of science: entropy. Now, entropy has a reputation for being confusing. The word often appears in discussions about thermodynamics, cosmology, information theory, and the fate of the universe. It gets described as disorder, randomness, chaos, uncertainty, and several other things besides. All of those descriptions capture part of the picture, but none tell the whole story. Fortunately, for tonight's journey, we don't need advanced mathematics. We only need a simple observation. Many processes in nature seem to move in one preferred direction. A glass falls and shatters. It does not spontaneously leap upward and reassemble itself. An ice cube melts in a warm room. It does not suddenly pull heat from the air and become frozen again. A drop of ink spreads through water. It does not naturally gather itself back into a neat little droplet. These examples may seem ordinary, but they reveal something profound. The universe appears to have a direction, not a direction in space, a direction in time, and entropy is deeply connected to that direction. To understand why this matters for white holes, let's slow down and look more carefully at what entropy actually means. Imagine a brand new deck of playing cards. Every card sits in perfect order. Ace through king, suit after suit, everything arranged neatly. Now shuffle the deck thoroughly. Cards scatter into a seemingly random arrangement. Which state is more likely? The ordered deck or the shuffled deck? Clearly the shuffled one. There are vastly more ways for a deck to be disorganized than organized. That's the key insight. Entropy isn't really about chaos in some dramatic sense. It's about probability. Some arrangements are vastly more common than others. Nature tends to move toward the more probable arrangements. The ordered deck becomes disordered because there are countless disordered possibilities and only a tiny number of ordered ones. The same principle applies throughout the universe. Heat spreads out. Energy disperses. Systems evolve towards states that can exist in many different configurations. This tendency is captured by the second law of thermodynamics. In simple terms, entropy tends to increase, not always in every tiny local situation, but overall, again and again, across stars, across planets, across galaxies, across the observable universe itself. The law has proven extraordinarily reliable. Physicists trust it because nature keeps confirming it. Every experiment, every observation, every technological application. The second law continues to work. And that's where white holes begin running into trouble, because a white hole appears suspiciously similar to a process running backward. Imagine watching a video of a black hole. Matter falls inward. Energy crosses the event horizon. Everything moves toward the center. Now reverse the footage. Matter bursts outward. Energy emerges. Objects move away from the center. The reversed video starts looking remarkably white hole-like. That observation may sound harmless, yet it creates a profound problem. Many processes allowed by fundamental equations become extraordinarily unlikely once entropy enters the picture. Let's return to the shattered glass. The laws governing individual molecules do not explicitly forbid every fragment from flying back together. The equations themselves allow it. The issue is probability. The odds are so absurdly tiny that we never observe it. A white hole often appears to occupy a similar position. The mathematics may allow it. Nature may not favour it. And in physics, those are very different things. This distinction is crucial. One of the biggest misconceptions about science is the belief that if equations permit something, reality must eventually produce it. Not necessarily. Many mathematical possibilities never appear in nature. White holes may belong to that category, or they may not. The debate continues precisely because nobody knows. What we do know is that entropy seems to oppose the kind of behaviour white holes represent. To see why, imagine a cloud of gas floating in space. Left alone, the gas spreads out. Particles move in different directions. The cloud becomes more diffuse. Entropy increases. Now imagine the reverse. A diffuse cloud spontaneously gathers itself into a smaller, more organised structure. Possible according to microscopic laws? Technically, yes. Probable? Not at all. Nature overwhelmingly favours the first scenario. The same logic appears when considering white holes. A black hole forms through gravitational collapse. Matter falls inward. Energy becomes concentrated. The process arises naturally from known physical mechanisms. A white hole seems to require the opposite. Matter emerges in an organised way. The system behaves as though the universe suddenly decided to reverse a process that normally proceeds only one way. That's a difficult idea to reconcile with thermodynamics. In fact, some physicists have argued that entropy may effectively prohibit stable white holes, not because a law explicitly forbids them, because maintaining a white hole would require extraordinarily special conditions that seem unlikely to occur naturally. This brings us to one of the most fascinating concepts in modern science. The arrow of time. You've probably heard the phrase before. The arrow of time refers to the fact that time appears to move in one direction. We remember yesterday. We do not remember tomorrow. We grow older. We do not grow younger. Stars burn fuel. They do not unburn it. The universe appears to possess a preferred temporal direction. Remarkably, this direction seems connected to entropy. As entropy increases, time appears to move forward. If entropy somehow decreased universally, many familiar distinctions between past and future would become difficult to define. White holes seem deeply entangled with this issue. A black hole fits comfortably into the ordinary arrow of time. Matter enters. Entropy increases. Everything behaves as expected. A white hole feels different. It resembles a process running against the thermodynamic current, like watching smoke return to a cigarette or cream leap out of coffee and back into the carton. Again, the comparison isn't perfect, but it captures the intuition many physicists experience. White holes feel thermodynamically unnatural. That feeling became stronger as researchers learned more about black holes themselves. During the 1970s, physicists including Jacob Bekenstein and Stephen Hawking made astonishing discoveries regarding black hole entropy. Before their work, black holes seemed surprisingly simple. Mass, charge, spin. That was largely it. Then researchers realized black holes possess entropy, enormous amounts of it. In fact, the entropy associated with a black hole is proportional to the area of its event horizon. This result transformed black hole physics. Suddenly, black holes became thermodynamic objects. They possessed temperature, entropy, energy exchange. The connections between gravity and thermodynamics grew deeper than anyone had expected. And those connections created additional difficulties for white holes. If black holes naturally fit into thermodynamic descriptions, what about white holes? How should their entropy behave? Would it decrease, increase, remain constant? Different theoretical models produced different answers. No consensus emerged. The puzzle became yet another reason researchers remained cautious. Interestingly, some physicists turned the problem around. Instead of asking whether entropy forbids white holes, they asked whether white holes might teach us something about entropy itself. After all, black holes forced scientists to rethink information, thermodynamics, and space-time. Perhaps white holes could reveal additional insights. This possibility became especially attractive when the black hole information paradox entered the picture. The information paradox emerged because black holes seemed capable of destroying information. Quantum mechanics strongly dislikes that idea. According to standard quantum theory, information should be preserved. Yet black holes appear to threaten that principle. Physicists spent decades debating possible solutions, and surprisingly, white holes occasionally appeared among the proposed answers. Imagine matter entering a black hole. Instead of being lost forever, perhaps the information eventually re-emerges. Perhaps the black hole transforms into a white hole. Perhaps the information escapes after enormous periods of time. The proposal remains speculative, yet it illustrates an important point. White holes survive in modern theoretical discussions not because evidence supports them strongly. They survive because they continue offering possible solutions to important problems. Whenever physicists encounter mysteries involving gravity, information, singularities, or quantum mechanics, white holes often reappear, not as established facts, as possibilities, as conceptual tools, as reminders that our understanding remains incomplete. Still, the entropy problem refuses to disappear. Every serious discussion eventually returns to it. Why does nature appear to favour black hole-like behaviour while avoiding white hole-like behaviour? Why does the arrow of time seem aligned with one but not the other? Why does entropy cooperate with gravitational collapse but seem hostile toward gravitational reversal? These questions remain open, and they connect to some of the deepest mysteries in science, because despite all our progress, nobody truly knows why the universe began in such a low entropy state. Nobody fully understands why the arrow of time points in the direction it does. Nobody possesses a complete theory unifying gravity and quantum mechanics. White holes sit at the intersection of all these unresolved issues. They challenge our assumptions. They expose gaps in our understanding. They force us to ask uncomfortable questions. And sometimes uncomfortable questions are exactly what science needs. The history of physics is filled with ideas that initially seemed impossible. Continents moving across Earth sounded absurd. Quantum mechanics sounded absurd. Black holes themselves sounded absurd. Most strange ideas turn out to be wrong. A few turn out to be revolutionary. Nobody yet knows which category white holes belong to. For now, entropy remains one of their greatest obstacles. The arrow of time appears to push against them. Thermodynamics appears skeptical. Nature itself seems reluctant to cooperate. Long before white holes became connected to wormholes, information paradoxes, or theories about the birth of the universe, another revolution was quietly reshaping physics. A revolution so strange that even the scientists who created it often struggled to believe it. Quantum mechanics. If general relativity transformed our understanding of gravity, quantum mechanics transformed our understanding of reality itself. And unlike many scientific theories, quantum mechanics didn't merely add new information. It challenged some of the most basic assumptions people held about how the universe works. Particles behaved like waves. Waves behaved like particles. Objects seemed capable of existing in multiple states simultaneously. Outcomes became probabilistic rather than certain. Reality, at least on very small scales, turned out to be far stranger than anyone had imagined. For decades, physicists lived with an uncomfortable situation. General relativity worked beautifully. Quantum mechanics worked beautifully. Yet the two theories seemed unwilling to cooperate. Each described a different aspect of nature. Each achieved astonishing success. And each appeared fundamentally incompatible with the other. Most of the time, this wasn't a serious problem. When studying planets, stars, and galaxies, general relativity performed wonderfully. When studying atoms, particles, and subatomic interactions, quantum mechanics excelled. The trouble appeared when both theories became important simultaneously. And nowhere does that happen more dramatically than inside a black hole. A black hole is essentially where gravity becomes so powerful that space-time itself reaches extraordinary conditions. General relativity predicts what happens remarkably well, up to a point. Eventually, however, matter becomes compressed into such extreme states that quantum effects should become impossible to ignore. That's where the trouble begins. The mathematics starts breaking down, theories start disagreeing, and physicists start reaching for coffee, lots of coffee. Because black holes occupy one of the most difficult frontiers in all of science. They sit precisely at the intersection where gravity and quantum mechanics must somehow be unified. Yet nobody possesses a complete theory of quantum gravity, at least not yet. This missing theory has become one of the greatest challenges in modern physics, and surprisingly, it is one of the main reasons white holes continue appearing in serious scientific discussions. To understand why, imagine falling into a black hole. This is not an experiment anyone recommends. The results would be difficult to publish. Nevertheless, let's imagine it. Classical general relativity tells us that collapse continues inward. Matter becomes denser. Space-time curvature increases. Eventually everything approaches the singularity. The singularity represents a point where density becomes infinite, and the equations stop making physical sense. For many physicists, this is a warning sign. Whenever infinities appear, alarm bells start ringing. Not because infinities are mathematically illegal, because they often indicate that a theory has reached the limits of its usefulness. Think of an old map showing unexplored territory. The map isn't necessarily wrong, it's simply incomplete. Many researchers suspect singularities represent something similar, a signal that deeper physics awaits, and that's where quantum mechanics enters the story. One of the central ideas in quantum physics is that nature contains fundamental limits. You cannot measure everything with arbitrary precision. You cannot compress information indefinitely without consequences. You cannot ignore quantum effects when scales become sufficiently extreme. Eventually quantum behavior matters, and inside black holes, conditions become about as extreme as the universe allows. This led many physicists to wonder whether quantum mechanics might prevent true singularities from forming. Perhaps collapse doesn't continue forever. Perhaps something else happens. Perhaps the singularity never actually exists. That possibility became increasingly attractive as researchers explored different approaches to quantum gravity. Among the most famous is a framework called loop quantum gravity. Loop quantum gravity attempts to describe spacetime itself using quantum principles. Instead of treating spacetime as perfectly smooth, the theory suggests it may possess a kind of discrete structure at incredibly tiny scales. Not unlike how a seemingly smooth beach is actually composed of individual grains of sand. From a distance, everything looks continuous. Up close, structure emerges. According to certain versions of this idea, space-time resists infinite compression. There is a limit, a point beyond which collapse cannot continue. If that's true, then something remarkable might occur inside black holes. Instead of matter collapsing forever toward a singularity, the compression eventually halts, then reverses, the process bounces. The word bounce sounds almost playful considering the circumstances. Yet it captures the essential idea. Gravity pushes inward. Quantum effects push back. Collapse stops. Expansion begins. And suddenly a possibility appears that sounds very familiar. What if a black hole eventually becomes a white hole? This concept gained attention because it offered a potential way around the singularity problem. No infinite density, no breakdown of physics, just a transition. An inward phase followed by an outward phase. A black hole evolving into something resembling its mathematical opposite. The idea remains speculative, very speculative. Yet it demonstrates how white holes re-entered mainstream theoretical discussions. Not because astronomers discovered them, not because evidence suddenly appeared, but because quantum gravity models kept generating them, again and again. The deeper researchers explored the quantum structure of space-time, the harder white holes became to completely dismiss. An especially interesting aspect of these models involves time. Remember how strange relativity becomes near black holes. Strong gravity dramatically slows time. To an outside observer, processes near the event horizon appear increasingly sluggish. This effect becomes extremely important in certain white hole scenarios. Imagine a black hole undergoing a quantum bounce. From the perspective of matter inside, the transition might happen relatively quickly. From the perspective of an external observer, however, enormous amounts of time could pass, millions of years, billions of years, perhaps longer. This creates a fascinating possibility. A black hole formed in the distant past might still appear ordinary to us today, yet internally, quantum processes could already be preparing a future transition. Eventually, after unimaginable timescales, the object might emerge as a white hole-like structure. The concept sounds almost science-fictional, yet it arises from legitimate attempts to combine gravity and quantum mechanics. Whether nature actually behaves this way remains unknown, but the possibility exists, and that's enough to keep researchers interested. Another reason quantum mechanics became important involves information. We've briefly touched on the black hole information paradox before, but it's worth examining more carefully. Quantum mechanics places enormous importance on information. According to standard quantum theory, information cannot simply disappear. Physical systems evolve, information transforms, but total information remains preserved. Black holes create tension with this principle. Imagine throwing information into a black hole, a book, a computer, a library, a civilization's entire accumulated knowledge. Everything crosses the event horizon. What happens next? Classically, the information appears lost, forever. Then Stephen Hawking introduced another complication. Black holes emit Hawking radiation. Over immense periods of time, they slowly evaporate. Eventually, they disappear. Now the paradox becomes severe. If the black hole vanishes completely, what happens to the information that entered? Quantum mechanics insists it must survive somehow. Classical gravity offers no obvious mechanism. Physicists have debated this problem for decades, and once again, white holes occasionally appear as possible solutions. Suppose information isn't destroyed. Suppose it remains trapped until some later phase. Suppose a black hole eventually transitions into a white hole. The information might re-emerge, not lost, not destroyed. Merely delayed. The proposal remains controversial, yet it illustrates why white holes remain scientifically useful. Even researchers who doubt their existence sometimes find themselves discussing them because they offer conceptual tools for addressing important questions. And information is about as important as questions get in modern physics. Quantum mechanics introduces another fascinating idea: vacuum fluctuations. The term sounds technical, but the basic concept is surprisingly simple. Empty space isn't truly empty. Even the vacuum contains activity. Particles and antiparticles appear and disappear. Fields fluctuate. Quantum uncertainty never completely vanishes. Reality remains restless even in apparent emptiness. This insight transformed how physicists think about black holes. It helped lead Hawking toward his discovery of black hole radiation, and it suggested that quantum effects might dramatically alter spacetime under extreme conditions. If quantum fluctuations can influence black holes, perhaps they can influence white holes as well. Perhaps space-time itself behaves differently at tiny scales than classical relativity predicts. Perhaps entirely new phenomena emerge. Again, certainty remains elusive, but possibilities multiply. One of the most intriguing developments in recent years involves attempts to understand space-time as an emergent phenomenon. Rather than treating space-time as fundamental, some theories suggest it may arise from deeper quantum structures, a bit like temperature emerging from countless molecular motions. Individual molecules don't possess temperature, large collections do. Similarly, space-time might emerge from underlying quantum relationships. If that idea proves correct, then black holes and white holes could represent different phases of deeper processes we don't yet fully understand. What currently appear to be distinct objects might eventually reveal themselves as aspects of a larger framework. A framework connecting gravity, information, quantum mechanics, and space-time itself. This possibility excites many theoretical physicists because it hints at unification. For over a century, physics has pursued unification relentlessly. Electricity and magnetism became electromagnetism. Space and time became spacetime. Researchers continue seeking deeper connections. Perhaps black holes and white holes participate in that story as well. Perhaps they're not opposites in the simple sense people often imagine. Perhaps they're stages within larger processes, transitions rather than destinations, transformations rather than separate entities. No one knows, and that's the important point. Quantum physics has not proven white holes exist. Far from it. What quantum physics has done is make the situation more complicated. Classical arguments against white holes once seemed relatively straightforward. Then quantum gravity entered the conversation. New possibilities emerged. Old assumptions weakened. Questions multiplied. White holes became harder to dismiss completely. At the same time, they remained difficult to confirm. The result is a fascinating scientific limbo. White holes are neither accepted reality nor discarded fantasy. They occupy a middle ground, a territory of active speculation, a region where mathematics, gravity, and quantum mechanics intersect. Imagine telling an astronomer from the 1960s that one day physicists would seriously discuss the possibility that black holes might not be permanent, not merely evaporate, not simply fade away, but potentially transform into something resembling their own opposite. The idea would have sounded extraordinary, perhaps even reckless. At the time, black holes were already strange enough, objects from which nothing could escape. Regions where gravity became so powerful that space-time itself folded inward. Cosmic endpoints, cosmic prisons, cosmic destinations with no return ticket. Yet over the past several decades, developments in quantum physics have forced scientists to reconsider assumptions that once seemed secure. And among the most surprising questions to emerge is this: could a black hole eventually become a white hole? At first glance, the answer seems obvious. Surely not. A black hole traps matter. A white hole ejects matter. One swallows, the other expels. One appears to represent an ending, the other resembles a beginning. How could one possibly become the other? The answer, if there is one, lies in a problem we've encountered several times already. The singularity. For much of the 20th century, physicists treated the singularity as the inevitable destination inside every black hole. Matter collapses, density increases, compression continues. Eventually, everything reaches an infinitely dense point. End of story. The problem is that physics tends to become suspicious whenever infinities appear. Imagine building a theory that predicts a car accelerating infinitely fast, or a room becoming infinitely hot, or a glass containing infinite amounts of water. You would immediately suspect something had gone wrong, not necessarily because the mathematics is incorrect, because reality itself rarely appears to contain infinities. Infinities often signal missing knowledge, a warning sign rather than a destination. Many physicists view black hole singularities in exactly this way. The singularity may not represent something real. It may represent the place where our current theories stop working. And if that's true, then the story inside a black hole could be very different from what classical relativity predicts. This possibility became increasingly attractive as researchers searched for a theory of quantum gravity. Quantum gravity remains one of the greatest unfinished projects in modern science. General relativity describes gravity beautifully. Quantum mechanics describes microscopic reality beautifully. Yet combining them remains extraordinarily difficult. Black holes sit precisely where both theories should matter simultaneously. Gravity becomes extreme. Quantum effects become unavoidable. Neither theory can safely ignore the other. And that's where some fascinating ideas began appearing. Suppose matter falling into a black hole never reaches infinite density. Suppose quantum effects intervene first. As matter becomes increasingly compressed, quantum forces grow stronger. Eventually, those forces become powerful enough to halt further collapse. Gravity continues pushing inward. Quantum effects push outward. The two compete, and eventually quantum effects win. The collapse stops. Then something remarkable happens. The process reverses. Instead of continued compression, expansion begins. Instead of inward motion, outward motion appears. Instead of a singularity, a bounce occurs. The word bounce sounds surprisingly gentle considering the circumstances. After all, we're discussing one of the most extreme environments in the universe. Yet that simple word captures the essence of the idea. Matter falls inward. Compression reaches a limit. Quantum physics prevents further collapse. The system rebounds. A cosmic spring compressed to its maximum extent suddenly pushes back. And once physicists started describing black holes this way, a startling possibility emerged. What if the rebound eventually produces a white hole? Suddenly, black holes and white holes no longer look like completely separate objects. They begin resembling different phases of a single process. A black hole becomes the inward stage. A white hole becomes the outward stage. One follows the other. The idea gained significant attention through work associated with loop quantum gravity. As we discussed previously, loop quantum gravity suggests space-time itself possesses a quantum structure. Instead of being infinitely smooth, space-time may contain fundamental building blocks at incredibly tiny scales. This structure naturally resists infinite compression, and if infinite compression becomes impossible, singularities become unnecessary. The black hole doesn't end in a singularity, it transitions. The implications are profound. Imagine watching a star collapse into a black hole. To outside observers, the black hole forms normally. Nothing unusual happens. Years pass. Millions of years pass, perhaps billions. The black hole continues existing. Everything appears ordinary. Yet deep inside, hidden beyond the event horizon, quantum processes are unfolding. Matter remains compressed. Time behaves strangely. Space-time undergoes extraordinary distortions. Eventually the system reaches a critical point. The black hole transforms. A white hole-like phase begins. Matter starts emerging. The process reverses. What once swallowed now releases. What once trapped now expels. The black hole becomes something new, at least in theory. There's an important complication here. Actually, several. The first involves time. Near black holes, time behaves in ways that challenge intuition. Strong gravitational fields slow time dramatically. This effect isn't speculation, it's a measured consequence of relativity. Clocks near stronger gravity tick more slowly than clocks farther away. Near a black hole, the effect becomes enormous. This creates one of the strangest aspects of the black hole to white hole idea. The bounce might happen relatively quickly from the perspective of matter inside. Yet from the perspective of distant observers, the process could require astonishingly long periods. Millions of years. Trillions of years. Perhaps longer than the current age of the universe. Imagine setting a timer that won't ring until long after every star currently shining in the sky has disappeared. That's the kind of timescale some models predict. As a result, even if black holes eventually become white holes, the transformation might be so slow that humanity never witnesses one. The universe itself may not yet be old enough. This creates an interesting situation. The theory becomes difficult to test, not impossible, just difficult. A prediction occurring trillions of years in the future poses obvious challenges for experimental verification. Physicists therefore search for indirect evidence, clues, patterns, observational signatures, anything capable of distinguishing these models from competing explanations. So far, the evidence remains inconclusive. The idea survives because it remains mathematically plausible and physically intriguing, not because observations have confirmed it. Another reason the proposal attracted attention involves information. The information paradox continues haunting black hole physics. Let's revisit the problem. Imagine throwing a book into a black hole. The book contains information. Words, ideas, patterns, knowledge. The book disappears beyond the event horizon. Then the black hole slowly evaporates through Hawking radiation. Eventually the black hole vanishes entirely. Where did the information go? Quantum mechanics insists information cannot simply disappear, yet black holes seem determined to hide it. This conflict has generated decades of debate. One possible solution involves white holes. Suppose information isn't destroyed. Suppose it's merely delayed. Matter enters the black hole. Information remains trapped. The black hole evolves. Eventually a white hole phase occurs. The information re-emerges. Nothing is lost. The universe preserves its bookkeeping. The paradox weakens. Not everyone agrees this works. Far from it. The information paradox has inspired numerous competing solutions. Firewalls, holography, black hole complementarity, quantum extremal surfaces. The list is long, yet white hole transitions remain among the more imaginative proposals, and importantly they're motivated by serious physics rather than mere speculation. Another fascinating aspect involves scale. Many people imagine black holes as gigantic objects. Some certainly are. Supermassive black holes contain millions or billions of solar masses, yet smaller black holes may be even more interesting in this context. Certain theories suggest tiny primordial black holes could have formed during the early universe. These objects would be far smaller than stellar black holes, and smaller black holes evolve more quickly. If black hole to white hole transitions occur, primordial black holes might potentially undergo them sooner. This possibility has inspired researchers to search for unusual astrophysical signals, perhaps brief bursts of radiation, perhaps unexplained transient events, perhaps phenomena not fitting conventional categories. So far, nothing definitive has emerged. Still, the search continues. One of the most appealing features of the black hole to white hole idea is its economy. Physics often values explanations capable of solving multiple problems simultaneously. If one mechanism addresses singularities, information loss, and white hole formation all at once, researchers naturally pay attention. The proposal doesn't merely create white holes, it potentially explains why white holes are so difficult to observe, because they wouldn't exist independently. They would emerge only from black holes after immense periods. Rare, brief, difficult to detect. The absence of observations becomes less surprising. The theory gains a certain coherence. Whether that coherence reflects reality remains another question entirely. History teaches caution. Physics contains many elegant ideas that ultimately proved wrong. Nature does not reward beauty consistently. Sometimes beautiful theories fail, sometimes ugly theories succeed. Evidence remains the final judge. For now, evidence has not delivered a verdict. Still, it's remarkable how much the conversation has changed. Earlier generations often treated white holes as purely mathematical curiosities. Interesting perhaps, relevant perhaps, but disconnected from physical reality. Modern quantum gravity discussions have altered that perception. White holes no longer appear solely as exotic opposites of black holes. Instead, they increasingly appear as potential future stages, possible outcomes, natural consequences of deeper processes, not separate objects, transformations. This shift may prove important regardless of whether white holes actually exist. Even if future research ultimately rejects them, the investigation has already generated valuable insights. Questions about spacetime, questions about quantum mechanics, questions about information, questions about gravity. White holes continue serving as useful guides through territory we don't yet fully understand. One of the reasons black holes became so important to modern physics has very little to do with gravity. That may sound strange. After all, black holes are often described as the ultimate gravitational objects. They bend space-time dramatically. They trap light. They dominate their surroundings through immense gravitational influence. Yet one of the biggest debates surrounding black holes concerns something far less obvious: information. And surprisingly, this debate is one of the main reasons white holes continue appearing in serious scientific discussions. To understand why, let's begin with a simple idea. Imagine a library. Inside that library are millions of books. Every book contains information, stories, scientific discoveries, historical records, poetry, maps, recipes, personal letters, entire civilizations recorded in ink and paper. Now imagine taking every single book and feeding it into a black hole. The library disappears, the shelves disappear, the building disappears, everything crosses the event horizon. What happens to the information? At first glance, the answer seems easy. The information falls into the black hole. Problem solved. Except it isn't. Because physics has very strong opinions about information, particularly quantum physics, and quantum physics insists on something remarkable. Information cannot simply vanish. That statement turns out to be one of the most important principles in modern science. The details are complicated, but the basic idea is straightforward. Physical systems evolve, they change, they transform. Yet the underlying information describing those systems should remain preserved. If you know the complete state of a quantum system at one moment, the laws of quantum mechanics allow you, at least in principle, to determine its state at another moment. Information moves. Information changes form, information becomes scrambled, but it doesn't simply cease to exist. Black holes seem determined to challenge this principle, and that is where the trouble begins. For a long time, physicists believed black holes were relatively simple objects. According to classical relativity, once matter crosses the event horizon, only a few properties remain visible from the outside. Mass, charge, angular momentum. That's essentially it. Everything else disappears behind the horizon. The black hole doesn't appear to care whether you throw in a book, a computer, a piano, or a rubber duck. From the outside, only the total mass, charge, and spin matter. This observation led physicist John Wheeler to popularize a famous phrase: "Black holes have no hair." The statement sounds amusing, but it carried a serious meaning. Black holes seem to erase details. They seem to simplify reality. The rich complexity of the outside world appeared to vanish behind the event horizon. For a while, that didn't seem like a major problem. Then quantum mechanics entered the conversation. And shortly afterward, Stephen Hawking made one of the most important discoveries in modern theoretical physics. Before Hawking's work, many physicists imagined black holes as permanent. Matter falls in, nothing comes out, the black hole remains forever. Then Hawking realized something astonishing. Black holes are not completely black. Quantum effects near the event horizon allow them to emit radiation. Today we call this Hawking radiation. The concept initially shocked the scientific community. A black hole emitting radiation sounds almost contradictory, yet the calculations were persuasive, and over time Hawking's idea became one of the foundations of modern black hole physics. The implications were enormous. If black holes emit radiation, they lose energy. If they lose energy, they lose mass. If they lose mass, they eventually shrink. And if they continue shrinking, they eventually disappear. A black hole is no longer permanent. It evaporates, slowly, extraordinarily slowly, but inevitably. For stellar black holes, the process requires periods of time so immense that they dwarf the current age of the universe. Still, the conclusion remains: black holes die, and that creates a serious problem. Let's return to our library. Suppose every book falls into a black hole. The black hole survives for trillions upon trillions of years. Eventually it evaporates completely. Now ask yourself a simple question. Where did the information go? The library contained information. The black hole disappeared. The Hawking radiation emerging from the black hole appears random. No obvious trace of the books remains. No obvious trace of the stories remains. No obvious trace of the library remains. Information seems lost. Quantum mechanics strongly objects. Thus the black hole information paradox was born. For decades, this paradox became one of the most important unsolved problems in theoretical physics. Some of the brightest minds in science devoted years to it, and despite tremendous progress, debate continues even today. Different physicists proposed different solutions. Some argued information escapes through Hawking radiation. Others suggested information remains encoded on the event horizon itself. Some proposed entirely new principles governing black holes, and among these various ideas, white holes occasionally emerged as potential participants. Not because white holes had suddenly been discovered, not because astronomers found evidence for them, because they offered an intriguing possibility. What if information isn't destroyed? What if information is merely delayed? Imagine a black hole forming. Matter falls inward. Information enters. Nothing escapes. For enormous periods of time, the information remains hidden. Then something unexpected happens. The black hole transforms. A white hole phase begins, matter emerges, energy emerges, information emerges, nothing was lost. The universe simply took an extraordinarily long time to return it. This idea is fascinating because it transforms the role of white holes. Instead of being isolated cosmic oddities, they become potential information release mechanisms. The black hole stores information. The white hole returns it. The paradox weakens. The bookkeeping balances, at least in principle. Of course, turning this appealing narrative into rigorous physics is another matter entirely. The details are enormously complicated, and many researchers remain unconvinced. Yet the idea illustrates why white holes continue appearing in modern discussions. They provide a potential route through one of the biggest puzzles in theoretical physics. Another way to appreciate the problem is through a simple analogy. Imagine taking a large jigsaw puzzle. Now place the completed puzzle inside a powerful blender. Turn the blender on. The pieces become scattered and mixed. The original image disappears, yet the information still exists. The pieces remain. Given enough patience, the puzzle could theoretically be reconstructed. The information was scrambled, not destroyed. Many physicists suspect something similar may happen inside black holes. Information becomes extraordinarily scrambled. So scrambled that recovering it appears impossible. Yet perhaps it never truly disappears. Perhaps the universe retains it somehow. The challenge lies in identifying the mechanism. Where is the information stored? How is it preserved? How does it eventually reappear? These questions have generated entire fields of research. One particularly influential development came from the holographic principle. This idea emerged partly through attempts to understand black hole entropy and information. Very roughly speaking, the holographic principle suggests that information describing a volume of space may be encoded on its boundary. The concept sounds bizarre, yet it has become deeply influential in theoretical physics. Some researchers believe it may provide important clues regarding black holes. If information can be stored on boundaries, perhaps event horizons play a more active role than originally imagined. Perhaps information never truly disappears behind the horizon. Perhaps it's encoded in ways we don't yet fully understand. Again, white holes occasionally enter these discussions, because any mechanism allowing information to re-emerge naturally invites questions about white hole-like behavior. What appears trapped forever might eventually return. The relationship between black holes and white holes becomes increasingly difficult to separate. Interestingly, the information paradox has transformed significantly over the years. At first, many researchers worried information might genuinely be destroyed. Today, most physicists suspect information survives somehow. The debate now focuses more on how survival occurs. Different camps advocate different mechanisms, different theories emphasize different principles. The conversation has evolved. Yet white holes remain relevant because they offer one of the more dramatic possibilities. A future phase in which hidden information becomes accessible again. This possibility becomes even more intriguing when combined with quantum gravity. As we discussed previously, some quantum gravity models replace singularities with bounces, collapse stops, expansion begins, black holes transition into white holes. If such transitions occur, information preservation becomes easier to imagine. Matter enters, information enters. The system evolves. Eventually the information reappears. Nothing is lost. The universe remains consistent with quantum principles, at least conceptually. Whether nature actually works this way remains uncertain, and uncertainty remains the defining feature of white hole research. What's remarkable is how the discussion has changed over time. Originally, white holes emerged from mathematical solutions to Einstein's equations. They seemed like curiosities, interesting perhaps, but disconnected from reality. Then black hole thermodynamics appeared. Then Hawking radiation appeared. Then the information paradox appeared. Each development created new reasons to revisit old ideas. White holes survived because they continued offering potential answers, not definitive answers, potential ones. And in theoretical physics, potential answers often deserve attention, especially when the questions are important enough. The information paradox certainly qualifies. After all, if black holes can destroy information, something fundamental about quantum mechanics may need revision. If quantum mechanics remains correct, then black holes must preserve information somehow. Either outcome is profound. Either outcome teaches us something important about reality. And that's why physicists continue debating these issues so passionately. The stakes are enormous. We're not merely discussing exotic objects in distant regions of space. We're discussing the consistency of modern physics itself, the relationship between gravity and quantum mechanics, the nature of information, the structure of spacetime. White holes happen to sit near the center of these discussions because they offer one possible bridge between competing ideas. Not necessarily the correct bridge, but a bridge worth examining. Much earlier in our journey, we asked a simple question. What would happen if a white hole existed? Since then, we've followed the idea through Einstein's equations, wormholes, entropy, quantum gravity, and the information paradox. Along the way, the concept has become increasingly complicated. At first, white holes seemed almost straightforward. Take a black hole, reverse it, problem solved. Now, however, we've arrived at a very different picture. White holes are no longer simple opposites. They are theoretical possibilities, potential consequences of deeper physics, mathematical structures that may or may not correspond to reality. And that brings us to an important question. Why are most physicists still skeptical? After all, we've spent quite a long time discussing white holes. The equations permit them. Certain quantum gravity models produce them. Some information preservation ideas seem to benefit from them. So why hasn't the scientific community embraced them? Why do most researchers remain unconvinced? The answer is surprisingly simple. Physics is not merely about what can happen. It's about what probably does happen. That distinction matters enormously. The universe contains many mathematical possibilities. Not all of them become physical realities. And when physicists examine white holes closely, several problems appear. Some are observational, some are thermodynamic, some are practical. Together they create a formidable collection of objections. Let's begin with the most obvious one. Nobody has ever seen a white hole. That fact alone doesn't automatically kill the idea. Remember, there was once a time when nobody had observed black holes either. Science frequently predicts things before discovering them. Neptune was predicted before it was observed. Antimatter was predicted before it was observed. Gravitational waves were predicted before they were observed. History teaches patience. Still, patience has limits. Black holes eventually accumulated evidence. White holes have not. The longer a prediction remains unsupported, the more cautious scientists become, and caution is generally a healthy habit in physics. The second problem involves formation. Nature seems perfectly capable of making black holes. Massive stars collapse, gravity wins, black holes form. The process makes sense. Astronomers observe each stage, the story hangs together. White holes lack an equally convincing formation mechanism. If you asked an astrophysicist how a black hole forms, you'd receive a detailed explanation. If you ask how a white hole forms, the answer becomes considerably less certain. Some theories propose quantum bounces, some propose exotic spacetime structures, some propose early universe phenomena, but none enjoy anything close to the consensus supporting stellar collapse. This matters because scientists generally prefer explanations connected to known physical processes. Black holes fit naturally into modern astrophysics. White holes often feel imported from somewhere else. The third issue involves stability. Imagine placing a white hole inside the real universe, not a mathematical universe, the actual universe, the one filled with gas, dust, radiation, cosmic rays, stars, galaxies, and countless wandering particles. Immediately a problem appears. Matter approaches the white hole. According to its theoretical description, nothing can enter. Not a single particle, not a single photon. The white hole must somehow reject every incoming interaction. Many physicists find this difficult to accept. The universe is messy, extremely messy. Things collide constantly. A structure requiring perfect isolation seems inherently fragile. Some calculations suggest even tiny disturbances could destabilize white holes. If that's true, then stable white holes become extraordinarily unlikely. The universe simply doesn't provide the quiet conditions they seem to require. Then there's entropy. Entropy has been causing trouble for white holes throughout this entire discussion, and it continues doing so here. Most processes we observe move toward greater entropy. They move with the arrow of time. White holes often appear to move against it, not necessarily violating physical laws, but behaving in ways that feel thermodynamically unnatural. That word matters. Unnatural, not impossible. Nature occasionally produces improbable events. The question is whether white holes are merely improbable or effectively forbidden by realistic conditions. Many physicists suspect the latter, not because equations explicitly ban them, because the universe seems to strongly prefer alternative outcomes. There's another issue as well. Scientific economy. Researchers generally avoid introducing new entities unless necessary. This principle has guided science for centuries. If ordinary physics explains an observation, there's little reason to invoke exotic alternatives. White holes face a difficult challenge here. Most phenomena once proposed as white hole candidates eventually received more conventional explanations. Gamma ray bursts, unusual transient events, high-energy astrophysical signals. Again and again, standard models proved sufficient. White holes became unnecessary, and unnecessary ideas tend to struggle. Not because they're wrong. Because science prefers simpler explanations whenever possible. This doesn't mean white holes have been discarded entirely. Far from it. Many respected physicists continue investigating them, especially within quantum gravity research. The key point is that interest and acceptance are not the same thing. A scientist can find an idea fascinating while remaining skeptical of its reality. White holes occupy exactly that position. Interesting, worth studying, not yet convincing. In a sense, white holes have become victims of their own strangeness. Every time researchers try to make them realistic, new complications appear. Every time one problem is addressed, another emerges. The concept survives. The certainty does not. Yet despite all these objections, let's set skepticism aside for a moment. After all, one of the pleasures of science is exploring possibilities. So let's imagine that nature surprises everyone. Let's imagine white holes really do exist. And let's imagine one exists relatively nearby. What would happen if you travel toward it? This is where things become especially interesting. Suppose you possess an impossibly advanced spacecraft, not merely futuristic, almost absurdly futuristic, something capable of surviving conditions far beyond current technology. You point the spacecraft toward a confirmed white hole. the first thing you'd notice is brightness. Assuming the white hole continuously ejects matter and radiation, it would likely be extraordinarily luminous. Light would stream outward. Energy would pour into surrounding space. Depending on the model, the object might rival stars or exceed them. Approaching it would not feel like approaching a black hole. A black hole often reveals itself through darkness. A white hole would probably announce itself through brilliance. As you move closer, the outward flow becomes increasingly obvious. Particles rush away. Radiation streams outward. The surrounding environment becomes violent. Imagine standing directly beneath a gigantic waterfall. Now replace water with high-energy particles moving at extraordinary speeds. That's still probably an understatement. The closer you travel, the more hostile conditions become, and then you encounter the truly strange part, the horizon. For a black hole, the event horizon represents a boundary you can cross inward. Once crossed, escape becomes impossible. For a white hole, the situation reverses. You can approach, you can observe. But crossing inward becomes impossible. The horizon refuses entry. Every future path available to you leads away, not inward, away. This is one of the hardest aspects of white holes to visualize because everyday experience offers no equivalent. Doors open both ways, tunnels permit passage, rivers allow movement across them. White hole horizons behave differently. They function as one-way boundaries. The universe itself appears to reject entry. If you fired a probe toward the horizon, the probe would fail to enter. If you directed a beam of light toward it, the light would fail to cross. Everything gets turned away. Everything remains outside. The object continuously releases matter while refusing all incoming traffic. This behavior creates some peculiar consequences. Suppose you attempted to orbit the white hole. Depending on the details, stable orbits might still exist at sufficient distances. Gravity would continue operating. Space-time would remain curved. The white hole isn't necessarily anti-gravity. That's an important point. People sometimes imagine white holes pushing things away gravitationally. That's generally not the case. A white hole's defining feature is not repulsive gravity. It's the behavior of its horizon. The gravitational field may resemble that of a black hole with equivalent mass. This means your spacecraft could potentially orbit it while remaining outside the forbidden boundary. From that orbit, the view would be extraordinary, a brilliant source of radiation, a torrent of outgoing particles, a region of space-time behaving unlike anything else in the known universe. Yet the closer you examine the situation, the stranger it becomes. Where is the material coming from? How long has it been emerging? Why does the process continue? Every answer generates new questions. The white hole becomes less like an object and more like a mystery machine endlessly producing puzzles. Perhaps the most unsettling realization would involve causality. Normally, we expect causes to precede effects. A rocket engine fires, the spacecraft accelerates, a star explodes, radiation emerges, the sequence feels natural. White holes blur these intuitions. Material appears, the source remains hidden. The history remains inaccessible. You observe consequences without fully understanding their origin. It's one reason white holes have always felt slightly unsettling to physicists. Not because they break the laws of nature, because they challenge familiar narratives about how nature operates. Eventually, after observing the white hole long enough, you might reach the same conclusion many researchers have reached over the decades. The concept is fascinating. The mathematics is intriguing. The possibilities are remarkable. Yet something about it remains elusive. The idea never quite settles comfortably into the rest of physics. Perhaps that discomfort reflects a flaw in the concept, or perhaps it reflects a gap in our understanding. History provides examples of both, and that's precisely why the debate continues. Because white holes occupy a peculiar territory between established science and unanswered questions, a territory where certainty remains impossible, a territory where curiosity remains valuable. It's worth remembering where we started. A simple question. What is a white hole? At first, the answer seemed straightforward. A white hole is the opposite of a black hole. A black hole allows things to enter but not leave. A white hole allows things to leave but not enter. Simple, neat, memorable. But as often happens in science, the deeper we looked, the more complicated the story became. We discovered that white holes were not invented by science fiction writers. They emerged from real mathematics, real equations, real attempts to understand Einstein's description of gravity. We followed them through black holes, wormholes, quantum gravity, entropy, information paradoxes, and even speculative ideas about the origin of the universe itself. Along the way, something interesting happened. The original question gradually changed. Instead of asking whether white holes are possible, physicists increasingly found themselves asking something else. Does nature actually need them? That may sound like an unusual question. After all, the universe doesn't consult physicists before creating things. Nature doesn't sit down with a checklist. Stars are not approved by committees. Galaxies don't require permission. Black holes certainly didn't appear because scientists found them useful. Nature does whatever nature does. Yet the question remains important because scientific theories are judged not only by what they allow, but by what they require. Many ideas are possible. Far fewer are necessary. A necessity often determines which ideas survive. Consider black holes. Today, black holes are accepted because they explain observations. Astronomers see stars orbiting invisible massive objects. They observe gravitational effects. They detect mergers through gravitational waves. They photograph event horizon shadows. The evidence repeatedly points toward black holes. Nature seems to require them. Without black holes, many observations become difficult to explain. White holes occupy a very different position. For more than a century, physics has progressed remarkably well without needing them. Cosmology works without them. Stellar evolution works without them. Galaxy formation works without them. Observational astronomy works without them. Again and again, researchers find explanations that don't require white holes at all. This fact has profoundly influenced scientific opinion. Many physicists don't reject white holes because they appear impossible. Many reject them because they appear unnecessary. There's an important difference. An impossible idea is ruled out. An unnecessary idea simply lacks motivation. White holes often fall into the second category. Suppose tomorrow someone proved that stable white holes do not exist. What would happen? Remarkably little. Most of modern astrophysics would continue functioning exactly as before. The standard model of cosmology would remain intact. Black hole observations would remain intact. Stellar evolution would remain intact. The vast majority of current science would survive unchanged. That's not usually what happens when an idea plays a central role in our understanding. Remove gravity and physics collapses. Remove atoms and chemistry collapses. Remove evolution and modern biology collapses. Remove white holes and most theories continue operating normally. This doesn't mean white holes are irrelevant. Far from it. It means their importance lies elsewhere. White holes are valuable because they illuminate areas where our understanding remains incomplete. In many ways, white holes function like flashlights, not because they provide answers, because they reveal questions about information, questions about singularities, questions about quantum gravity, questions about the relationship between space and time, questions about the ultimate fate of black holes. Whether white holes exist or not, those questions remain. And that's one reason researchers continue studying them. Sometimes an idea proves useful even if nature never realizes it physically. History contains many examples. Physicists routinely explore hypothetical universes, imaginary particles, alternative geometries, mathematical structures, not because they expect all of them to exist, because exploring possibilities often reveals hidden assumptions. White holes have served that role exceptionally well. For over a century, they have forced scientists to examine their understanding of space-time more carefully. They have exposed weaknesses in existing theories. They have highlighted tensions between gravity and quantum mechanics. They have challenged assumptions about entropy and the arrow of time. Even if white holes never exist physically, they have already influenced physics significantly. Yet there is another perspective worth considering. Sometimes nature surprises us. In fact, nature has a habit of doing exactly that. Imagine travelling back 100 years. You tell scientists that space itself expands. Many would be skeptical. You tell them black holes exist. Many would be skeptical. You tell them invisible dark matter dominates galaxies. Many would be skeptical. You tell them gravitational waves will one day be detected using instruments capable of measuring distortions smaller than atomic nuclei. Many would be skeptical. And yet all of those things eventually became accepted science. The lesson is not that every strange idea turns out to be true. Most don't. The lesson is that certainty should be handled carefully, especially when dealing with the frontiers of knowledge. White holes live on one of those frontiers. They occupy a region where our understanding becomes incomplete, a region where quantum mechanics and gravity begin colliding, a region where existing theories start showing cracks. Whenever physics approaches those boundaries, confidence naturally decreases, questions multiply, possibilities expand, and white holes repeatedly reappear, not because scientists desperately want them to exist, because the mathematics keeps generating them again and again. The persistence is remarkable. Think about how many opportunities physicists have had to discard white holes entirely. Decades have passed, new observations arrived, new theories emerged, entire fields evolved, yet white holes never completely disappeared. They remain controversial, they remain speculative, but they remain present, hovering at the edges of modern theoretical physics. That persistence may ultimately mean nothing, or it may mean something important. Nobody knows, and perhaps that's the most honest conclusion available. Because if there's one theme running through the entire history of white holes, it's uncertainty. Not ignorance, not confusion. Scientific uncertainty. The productive kind. The kind that drives research forward. The kind that motivates new observations. The kind that encourages better theories. Science often advances by learning which questions deserve asking. White holes have consistently generated good questions. What happens inside black holes? Can information truly disappear? Does space-time possess a quantum structure? Do singularities exist? How does the universe behave under its most extreme conditions? Those questions matter regardless of whether white holes exist, and that's part of what makes the subject so fascinating. Sometimes the value of an idea lies not in the answer it provides. Sometimes the value lies in the doors it opens. White holes have opened many doors. Some lead nowhere. Some lead toward active areas of research. Some may eventually transform our understanding of reality. At present, nobody can say which paths matter most. Perhaps future observations will discover phenomena best explained by white holes. Perhaps quantum gravity will reveal that black holes naturally evolve into white holes. Perhaps entirely new physics will emerge. Or perhaps future generations will conclude that white holes were mathematical possibilities never realized by nature. All of those outcomes remain possible, and that's perfectly acceptable. Science is not a machine for producing certainty on demand. It's a process for reducing uncertainty gradually. One observation, one experiment, one theory at a time. White holes remain part of that process. Not established facts, not pure fantasy. Possibilities. Possibilities sitting quietly between what we know and what we don't yet know. If you've noticed anything during this journey, it's probably that white holes become less simple the longer you examine them. The original idea sounds almost childishly straightforward. A black hole's opposite. Yet every layer reveals another question, another complication, another connection to deeper physics. By the end, white holes are no longer really about white holes. They're about the limits of our understanding. They're about the places where current theories stop providing clear answers. They're about what happens when humanity tries to understand a universe that often refuses to behave according to intuition. And perhaps that's fitting, because the universe has never shown much interest in matching human expectations. It routinely turns out stranger than our first guesses, sometimes stranger than our second guesses too. Whether white holes eventually join the list of real cosmic objects or remain elegant mathematical possibilities, they have already accomplished something worthwhile. They've reminded us that science is not merely a collection of facts, it's an exploration, a process, a continuing conversation between observation, theory, and curiosity. And somewhere out there, beyond the stars, beyond the black holes we know exist, beyond the boundaries of what current physics can confidently explain, there may still be surprises waiting. Maybe white holes are among them. Maybe they aren't. For now, the universe remains under no obligation to reveal the answer quickly, and perhaps that's part of what makes the question worth asking in the first place.